we can start our devices.
Yes, please start the device.
Okay.
Okay, so I think we, yes?
Around 10 o'clock, the management need my attention, so I may likely flip out for probably maximum of 30 to 40 minutes and I'll be back.
Okay.
I know I will lose a few, but I hope I'll catch up later then.
Sure. It's okay.
All right.
So without we delay no more, let's start the class for today. So, okay. So yesterday we are going through the SDP, spanning tree protocol. Okay, the spanning tree protocol. So we learned that if in layer 2, we have the redundant link where we interconnect the switches, maybe at least 2. If two switch will connect with 2 links. Okay, 2 links. Okay. Even there is only 2 switch with 2 link connected. Okay, this also will cause a loop. Okay, and then it will cause broadcast storm. Okay, broadcast storms, and also duplicate frames to be received by end stations, and also causing the MAC table instability, because the switch will keep on update the MAC address table. So in this situation, in your switch, you will see the warning message. It will say flapping port. Okay. So if this happens, if you have NMS, of course the switch will send NMS, send an alert message to the NMS system, and you'll be alert. You found that, oh, something happened, so you have to check. Okay, so to resolve the loop, we can use SDP. So SDP will logically block one of the ports in the network. So, but this is logically blocked. So block block one of the port to stop the redundant link. So if any of the active link is down, so the redundant link can become active. So the network can be, the SDP network can be converged again and become stable again. Everyone can connect to the network. Okay. So for an SDP network to be converged, first we have to run the elections to find out who is the root. So the switch with the lowest bridge ID will become the root. Okay, but when comparing the bridge ID, first we compare the bridge priority. Again, the switch with the lowest bridge priority will be the root. And if there's 2 or more switch with the same bridge priority, okay, all are the lowest, but they are same. So you have to compare the MAC address. The MAC address is confirmed because it can be the tiebreaker, because MAC address is confirmed is universal unique. Okay. So in here, the parameter we can manipulate, we can change is the bridge priority, so that we can force one of the switch we can decide which switch we want to become the root. So we can change the bridge priority to bridge priority lower, any numbers lower than 32768 because the bridge priority for all the switch by default is 32768. So we can change to 0. So we can confirm it. If 0, you can confirm that the switch will become the root. If we let other switch, their bridge priority remain at default. Okay, next, in SDP, we have this BPDU, configuration BPDU. So this configuration BPDU is sent by the root. Okay, it's actually at the elections phase. When there's elections, election process, all the switch send BPDU to each other to inform each other what is their bridge ID, so they can run the election, they can compare with each other. They try to find out which switch in the network has the lowest bridge ID. Okay, after they find out, after they decide the routes, and then they find out, they have to decide the port rows. So the port row on the switch, on the root switch, is always the designated port, because designated port is a port that always send BPDU to inform the downstream switch who is the root switch, who is the root switch or root bridge. So switch A here is the root switch or the, I just stick at root bridge. So then how they decide the port row is also based on the first parameter they compare is the root path cost. Root path cost means the lowest cost for the switch back to the root. So we can, example here, we know that switch B, the root path cost for switch B is 20,000, for C also 20,000. So between switch B and switch C, so which one to be the designated port, which one to be the alternate ports. So this will depends on, first they compare the root path cost, they're same, so we move to the next one, they compare the bridge ID. So the lowest bridge ID will be the designated port. The higher one will be the alternate ports. Okay, if the bridge ID also the same, like this, we can use the port ID. So the lowest port ID, okay, the ports that receive the BPDU with the lowest port ID will become the root port. The other one will become the alternate ports. Okay. So these are the process. So this is the port state transitions. So everyone start with disable, and then everyone go into blocking state. Everyone blocking states. That's the port blocking states. So, and then after 20 seconds, okay, blocking state is a state where the ports are waiting to receive BPDU, but there's no one sending. So they keep waiting for 20 seconds, which is the max H time. 20 seconds. After 20 seconds, everyone move into listening modes. Okay, listening state. At this state, everyone, all the designated port is starting to send BPDU. Is to run the election. Yes.
Sorry, Mr. Dave.
Yes.
Can you use your pen to indicate the delay periods?
The delay periods.
Between the delay, disabled and blocking, then blocking and listening and learning.
Okay.
Once again.
Blocking to listening is using the max H, the max H time. Max H, 20 seconds. Okay, after 20 seconds, everyone go into all the ports go into listening states. So in listening states is where the elections for the root bridge and the port rows to be decided. This is listening state. And this whole process is being given a buffer of 15 seconds of forward delay. Okay, 15 seconds forward delay. Let's put an FD, forward delay, 15 seconds. So after everything done, in 15 seconds, okay, the alternate port, the port to be alternate port will straight away switch change to blocking state. Then let's see, alternate ports. Or should I put that here? Alternate ports. Okay. Alternate port final state is blocking state, and if there is the port, if the port is become the decided to be designated port and root ports, they will go into learning state. Okay. Designated and root ports. We go to learning state. In learning states, they are trying to learn the MAC addresses. They are trying to populate, or the switch try to populate their MAC address table. Okay, so the processor, the period being given to learn the MAC address table, to learn the MAC address is also 15 seconds. Yes, yes.
Please, what do you mean of that FD?
Forward delay. The timer forward delay.
It's okay.
Okay. Let me put the name forward delay. Also 15 seconds by default. Okay. So so the final state, actually the final state for designated port and root port is forwarding. Okay, again. Designated and designated port and root port is forwarding states. So forwarding state, they start to forward user traffic. So you can see that the whole process, 20 seconds, 15 seconds, plus 15 seconds, total 50 seconds. In this 50 seconds, even though the switch is already boot up, but the user still cannot send any user traffic. Okay, so this is the issue that one of the issue of the SDP, because the time to conversion is slow. Okay, it's slow. So that's why we have enhanced version. We call it Rapid Spanning Tree Protocol (RSTP), which we'll look into in the next topic.
So it takes, Mr. B.
Yes.
So we can say that the recovery time for the root is a total of 50 seconds.
The
root for the root to recover.
For the roots to recover.
Is the round figure of the 50 seconds?
For roots to be recovered means when the root is failed. Root failed. Okay, well, that's now we are going to this. Okay. So after the STP converge, everything fine. Nothing happened. Everything stable. But somehow, someday, the root down. Okay, the root is down. So what happened? So all the switch will have to begin the election again to find out who is the new root. Reconvergence is initiated beginning with root elections. Okay, so this root failure. Yeah. So what if this is an indirect link failure? Means all this process, this root failure means that all the process here blocking to listening, learning, forwarding had to the process will begin. Actually, it starts begin from listening to learning and forwarding because I'm already in forwarding state or either blocking state. So for the ports that in blocking state, so sure they have to go through 20 seconds, 15, 15. So that depends on the situations. Okay. So indirect link failure. What if the switch, the root bridge is still alive, but this link is down? Switch B will thought that this link is down means that might be the root bridge. Switch B assume the root bridge is down. So what you try to do is same. You try to run the elections, begin the elections by sending his own BPDU. Try to propose, or you can say in this BPDU, you will state that the root ID in this BPDU will be the bridge ID of the switch B. We try to run the election to tell switch C, I am the new root. Okay, but since switch C, the connection between the root bridge and the switch C is still active, so switch C will still keep on receiving the BPDU from the root bridge. So here, but switch C also expecting to receive the BPDU from this direction, stating that in the BPDU will be the root ID. The root ID in the BPDU will be the bridge ID of the root, same as this one. This is what switch C expect to receive from this direction. But now what happened is switch B send the BPDU, okay, telling switch C, switch B is the root. Oops. So switch C might notice something happened. Okay, but what switch C will do is it will, even this is alternate port, right? So switch C keep on receiving the BPDU from switch B for, we wait for 20 seconds, the max age, 20 seconds. Okay. So 20 seconds, continue to wait. After 20 seconds, switch C will turn this port to designated port. Right. Okay, turn this port to designated port. Okay. So switch C will turn this port to designated port and send BPDU to switch B to tell switch B the root is still alive. The root is still here. Because switch C still receive the BPDU from the roots, and then every 2 seconds. So switch C also every 2 seconds send a new BPDU to the switch B to tell the root ID, who is the root. Switch A is the root, is still alive. Okay, now when the switch B is sending BPDU from this port, this is the port, correct? But now switch B found that, oh, the root, I can access the root, I can get to the root at this port. Okay, so it means that the root is still alive. So I will change my this access port to root port. Okay. So you can see that. So after change to root ports, you go into the for learning states. Okay, learning state 15 seconds. Then we go into the actually is when the switch is for the time switch is send the BPDU. So this is actually election already. So you'll be listening state 15 seconds, learning state 15 seconds. Okay, and then go into forwarding. This port go to forwarding state. Since this is already a designated port, this is also forwarding states. So what's the total time? At the time, this
Mr.
link is.
Mr. Bell.
Yes.
Please help to label the seconds, please.
Okay.
With your pen. Yeah.
Yes, with my pen. Again.
Yes, I said you should label the seconds.
Label the sequence.
Yes, the seconds is going to use. You know, you said yes, one you're going to use 20 seconds to
time.
Okay, understand.
Yes. Yeah.
Okay. So switch B, when the link is down. Okay, when the link is down, switch B send a BPDU, try to start the election. And here, switch C at this port, here wait for 20 seconds. Okay. Let me put, okay, 20 seconds. Here for 20 seconds. So after 20 seconds, the switch C will change this alternate port to designated port. Okay, after 20 seconds. Okay, then you will send a BPDU. Set BPDU to tell switch B. Try to run the election with the switch B. So then switch B will receive this. This BPDU, then we'll know that this is the switch A is still the root. Okay, so the root bridge. So switch B will turn his port from designated ports. When the switch when the initial phase state, the switch B try to run the election, it will need to change the port to designated ports so that it can send BPDU. After it learn this BPDU, the new BPDU sent by switch C, so we change the port to root ports, because this is the only path, only port it can go to the root bridge. So it takes 20 seconds for the switch C to change his port to designated ports. Okay, this is 20 seconds. Then they take 15 seconds for listening state. Listening state, because they run election between the B and C. Okay, and then there's listening state, 15 seconds again. And then after 15 seconds, they go to learning state. Learning state have to try to learn learn the MAC addresses at these ports. Okay, from this port. And then the learning state is being given 15 seconds also. So after 15 seconds, root port change to forwarding state. Designated port also change to forwarding state. So total also 20 seconds, 15 seconds, 15 seconds. 50 seconds. 50 seconds. Okay. So this is indirect link failure. How much time is needed for the SDP network to converge, to reconverge again? Is at least 50 seconds. Okay, in this topology. Okay.
50 seconds.
Okay, so we go to the next one. What is this direct link failure? What you mean by is when there's a switch with two direct connections, with two connections connect to the root. Okay, connect to the root. Okay, so initially this is a root port. This is alternate port. Nothing happened. Okay, stable. Suddenly, okay, the root port is down, or this link is down. Okay, this link is down. So switch B should know that, okay, my root port is down, means that I got my alternate ports. Alternate port is a backup for root ports. Once my root port down, I should change my my alternate port to root ports. So we don't need to run election. Understand? So we skip the 20 seconds. So switch B change the root port, the alternate port to root ports. Okay, and then under the root port, you still wait for the listening states. Okay, listening state, because it starts from the blocking state. Okay, alternate port blocking stage change to root port listening states, and then but you still need to wait. Okay, yeah. Okay, why the switch B, where's the root port, where the alternate port, when it changes to root port, it doesn't wait 20 seconds. Why? Because every 2 seconds the designated port of the root bridge is keep on sending the BPDU for every 2 seconds. So the alternate port will change to root port. It doesn't need to wait for the blocking state. The blocking state can change to once the blocking state receive the BPDU. So no need to wait for 20 seconds. Receive BPDU, it should change to listening state. So at listening state, still need to wait 15 seconds. Then only can change to for learning state. And learning state, again, need to learn the MAC address, and then wait 15 seconds, change to forwarding state. So in this kind of topology, a switch have two connection connect to the roots. This is for this kind of topology for the SCP to converge is at least 30 seconds. Okay, 30 seconds by default at the segment below right here. So this is different from this topology. Okay, it's different because in this topology, the root port of the switch is still up, nothing happened, but the problem is on the switch B. Okay. So next, topology change MAC instability. So when there's a topology change, when there's a link is down, so you can see that before this, before the link is down, where is B? Where is host B? In switch B MAC address, where is host B? BB is at G2. This is G2. So whenever host A want to send the frame, send the data to switch to host B, switch B will always send out from this port G2. But what happened now is at switch C, the root port is down. This link is down. Okay, so means that this port need to be up. But in switch B doesn't know anything about anything happened between this. The link is down. Switch B doesn't know this because the link is not directly connected to switch B. So switch B, the record in the MAC address table is still there. Okay. So what happened is, see, whatever host A want to send to host B is still send to switch B. Switch B still follow his own MAC address tables. Yeah, BB is at G2, still keep on sending to G2, but switch A knows that this link is already down. Whatever sent to the switch B, send to switch A.
Hello, Mr. Bear.
Yes.
Yeah, please. What is the function of the dotted line between switch B and C?
Dotted line is the redundant link.
Okay.
Redundant link. Okay. Redundant link blocked by the STP. Okay. So everything is still switch B still send everything to switch A.
Please,
Okay.
I have to label it, sir.
Okay. 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 So switch B still send everything to switch A. Switch A will drop everything. Okay. Drop all the frames that are designated for B. Okay. Because this link is already down. So what happened is the MAC address table entry is expire only after 300 seconds by default. Means that all the entry in the MAC address table, each of these have a timeout period of 300 seconds or 5 minutes. When the entry is being renewed, refresh, it can start countdown 300 seconds. Okay, 300 seconds. Okay, after 300 seconds, it will be flush. So each of the entry have its own timer. Okay, and then what happened here is the switch B had to wait the timer, the timeout for the MAC address, this entry to be expired, so that this record can be flushed. Then only the switch B can send broadcast all the frame that the destination MAC address is BB broadcast to this link, so that the frame can go to host B. So is any way so as here we hope that when the link is down, okay, switch B should flush away this record, whatever is sending to G2. We hope that we can do this. So this is what HTTP also can do. This is where we have this TCM BPD. Here comes the TCM BPD. Okay, so this is where we apply TCM BPD. topology change notifications to inform routes of topology change. Sent by who? So if there's, take an example, for this switch, something happened below. Something happened. Okay, something happened. So this switch will send a TCN BPDU. Okay, send a TCN BPDU. From where? From his root port. Okay, root port. Why? Because you want to inform the purpose of this TCN BPDU is to inform the routes something happened in the network. Okay, that's a topology change in the network. So the switch send the TCN BPDU to this switch. This switch will reply with a configuration BPDU, which is the TCA, the topology change acknowledgement, to acknowledge the TCN BPDU sent by the reports, so that he can stop sending the TCN BPDU. After that, this switch also send again a TCN BPDU to the routes. The route reply with a topology change acknowledgement BPDU, okay, to the switch to tell him, okay, I received your TCN BPDU, you can stop sending. After that, the route will send a BP configuration BPDU, the same BPDU, but if the flag, the TC bit here, topology change bit set to 1. Okay, set to 1. Okay, set to 1 is to tell everyone, there's a topology change in the network. Everyone please reset. I should mean set your all the MAC address record in the MAC address table. All the entries in the MAC address table set to 15 seconds. The timeout set to 15 seconds means everyone, because what happened is something happened at here, but this switch, this and and this they doesn't know anything or except this. This one still receive the TCN BPDU, but this three guy, this switch doesn't know anything. So they need the root. They need the root. It depends on the root to tell them there's a topology change in the network. So what they need to do, okay? Okay. So after the root send BPDU with the TC bit set to 1. So everyone, all the non-root, all the downstream switch receive the TCN receive the BPDU will reset all the MAC address table entry to 15 seconds. So means that instead of waiting for 300 seconds, now you just wait for 15 seconds, and then all the entry will be flushed away. And then switch B can send the frame destination for host B out to this port, so that when the host B reply, switch B can record the new entry. BB is now coming from G1. Okay, this way. BB is now G1. So this is how the STP speed up the again another process steps to speed up the STP reconversion. Okay, but this is still slow because you have 15 seconds. Can we have faster one? Huh? Yes, that's why we have the RSTP. Okay, let's continue. Before that, we're still in the STP. So next, some configurations. Okay, to set the STP modes, what's the configuration? The command STP mode, STP. That's all. Okay, next. So assigning the routes. Again, we can use STP. This is a system view. That's a system view. STP priority 4096, or in the stack of 4096. Let me show you. S1. System view STP priority question mark. Okay, bridge priority instead of 4096 means that the smallest number is 0. The second is 4096. So the third one will be 4096 plus 4096 is 8192. Okay, the next one is plus again, plus another 4096. So what happens if I type another one? If I type 100, wrong parameter. If I type priority 4096, it works. Okay, but this cannot work because the switch configured as the roots, primary root or secondary root. Okay, and use display this. I know that this one should already be primary. So okay, undo STP root. Okay, so now I can change the priority. 4096. Okay. This is this is the command STP priority. It's the command to change the bridge priority so that we can manipulate which enforce one on the root election, the switch to become the roots for the STP network. Okay. Okay. So after configure, you can display STP to check. Okay, then.
Hello, Mr. Bay?
Yes. Yes, please.
So in what increments are we having such an assignment?
4096. Okay, in steps of 4096. Means okay, the first one is 0. The second one, 4096.
Okay, I've seen it.
Okay. So after you configure, you can check. What's this? Okay. Display STP, you can mode STP, and then 4096.
Okay.
Because this is the bridge ID of this local switch. Okay. So again, STP mode, question mark. There are 3 modes you can choose. Okay, now it's already I'm running STP. So what you can do, you also can try to do again. If yesterday you haven't set the configuration, you can just try STP mode space STP. Do it on all these 3 switch. S1, S2. Yes.
Please excuse me. I will have to run for maybe 30 minutes to meet with management.
Oh, okay, sure.
Thank you.
Okay. See you later. Okay. So this is the command. And then path call standards. We also can change the path call standards. By default, it's running .1t. Okay. If there are standards, all the switch just follow the standard by following the ports, the speed of the ports. Okay, let's see this one. Display STP. Okay. So I can say port 1 is this is S1. The port 1 is not connected to anyone. Okay. Display STP. Try to find this is port G1. Press the space bar. Okay, this is port G2. This is port G2 is connected to S2. So what is this is a G port, gigabit port. So what is the cost? 20,000. Okay, 20,000. Can I change this? Yes, I can change. So if you change this, means that it will not follow you are not following the standards. Okay, you can change that. Let's see. For what is the status for now. Let's say display STP brief. Designated, okay. For S2, display STP brief. Root designated. So this will be S3 display STP brief. So root alternate designated, correct. So now I try to change someone. S3. So for S3, this port is the cost is 20,000. Say for S2, this port is 20,000. For S3 also, this port is 20,000. So if going this way is total 40,000. This way is 20,000. 20,000, and that's why S3 select this port as the root ports. Now, what I want to do is I change the cost of this port. So I change this to become greater than 40,000. Because this is for 20,000, 20,000. So if I change this to greater than 40,000, maybe 50,000, then the S3 will take this, become the root ports. This will be the alternate ports. Okay, let's do this. S3 G1. Okay. System view, interface G003. Should be 3. Sorry. Interface G003. STP. Let's see what's the command again. Cost. STP cost question mark. Okay, can set 1 until what is this? 200 million. Okay, STP cost does set something greater than 40,000. I can just set like this 40,001. Okay, also can. What's our, maybe I just set something very odd. I say 40,123. Okay. Now, what I expect is S3 G1 is now become the alternate port. G2 is the root port. Let's check. Display STP brief. Oops. Let's check. STP cost. To change. Alternate port. S2 is still the alternate port. Let me check. Is there something wrong? See G1 cost 2,000. To STP brief. Root is 1. Nothing changed. Display this STP instance. Display STP. Oh, 1 C1. Oops, nothing. So nothing is changed. Why? Let's see. Why nothing is changed? Okay, maybe I do something wrong. Never mind. I just undo the STP cost at first. STP cost, display this. Yeah, maybe I should configure at the sender side. Who will send the BPD? So we configure as S1. If I configure as S1, let's see. S1 interface G003 STP cost. Let's say 40,000. 40,123. Okay, and go to S3. Display SDP brief. Okay, see what we have now.
Mr. Robert,
Yes.
please mute your mic.
Yes.
Mr. Robert,
Okay.
please mute your mic. Thank you.
Okay, let me check. It doesn't work. Let me check again. Data G3. This something happened. G3, S3, S3. Oops. So I know what happened already. This I should undo SDP course. Nothing happened. Okay, it actually should be configured as S3, but I configured the wrong port. I should configure S3 G1. Okay, display this. I go to S3 G01. SDP course. Sorry. SDP course 40123. Okay, display SDP brief. Okay, now there's a topology change. So you can see SDP TC, topology change, sent out by, see, topology change. This is sent by the root to tell everyone. Okay, let me display MAC address table. Do we have anything? Nothing. Never mind. So what I want to show you is now, what is the port state, port row for now? Now, G1 is alternate port, G2 is root port. G1 is now alternate port, G2 is the root port. Okay. What happened? Because I changed the cost of this port to 40123. So, but this port is still, let's say, is still 20,000. So this port 20,000. So for S3, again for S3 to go from out from G1, go for G1, go to reach the root. The cost is 40123. So for S3 to go out from the G2 to go back to the roots is 20,000 plus 20,000. So coming from this 20,000, go out from here also 20,000. You doesn't need to add the in where the direction is going into. Going in doesn't count. Just going out. When going out, just count the cost on the going out. Okay. This. This. So you can manipulate the root port also. So this depends on your network design, how you want to do it. So here I just undo. Let me display SDP to show you what happened to the port G1. So this is the port G1, okay, G1, and then the active half cost is 40123. Okay, so if I just undo it, undo SDP cost, display SDP brief. topology change again. So you can wait some time here. So here it doesn't show any blocking or the listening. It won't show it here because this is the RSTP, or I should say this is the MSTP, the port state of RSTP and MSTP. This switch will not be able to show the port state for exactly port states for the SCP. Okay, later we'll see what do we mean by discarding state. Okay, again, now it's already converged again. G1 is root ports, G2 is alternate port. So next one, root protections. Root protection prevents changes to the topology as a result of root bridge transition caused by receiving higher priority VPD. Higher priority means the lower bridge priority number. Okay. So here this root protections is only can apply on designated port, which is on the root designated port, or maybe on this switch B and switch C, this is the designated port. So you only can the root protection will be only have effect when applied on the designated ports. So how the designated ports, how this root protection works is when the designated port with root protection receive a BPDU. A BPDU with a lower bridge priority, it will change to discarding state. So it will not let the stay at the designated port. It will not let the switch to change to steal the root bridge state. So this is to protect your root bridge, because there might be someone here might be hacker use his PC, use his maybe a laptop to generate BPDU. Because normally for PC, for antiviruses, they don't run election, they don't join the STP election, because STP election is just related to the switches. Okay, but if somehow a hacker can use some tools to generate the BPDU with a lower bridge priority, and then send into your network, so that it can steal the position to become the root. If the hacker becomes the root, means that your port, this might be a port being blocked, and then all your informations might be go this way. Okay, you have to pass through the network device. Maybe I can connect. The hacker can connect another switch. Okay, and here. So you might cause the traffic to go into the switch. Okay, so this is some security issue. So that's why we have these root protections. So you have to go into the designated port to apply STP root protection. Let me show you. So what I will do is I will apply STP root protection on G3 or S1, and then I will change the S3. Okay, the bridge priority of S3 to 0. But for now, what is the bridge priority of this STP? The STP. So now here. The bridge priority of the S1 is 4096. 4096. So if I change the S3 to 0, S3 will send a BPDU. Try to take over the root bridge position. So S1 G3 set STP roots. What's the command? Yeah, correct. STP root protection. Enter. Display STP brief. Now you can see on this port, on this designated port G3, there's a root protection. Root protection. Okay, now at S3, so S3 I change STP priority to 0. STP priority to 0, I can see this guy try to send his own root ID, his own bridge ID inside the root ID field in the configuration VPD. We try to run election. We want to become the new root. So that means I go to S1. What happened to S1? Display STP brief. See? The port G3, port G3 of S1 stay at designated port and discarding state. It doesn't care about the VPDU sent by the S3. Okay. So in S3, in the aspect of S1, display STP. So the root is this. Okay, the root is this. The root already changed to become the S3. Become S3, but because this is a security breach, so the S3 display STP brief stay at, but the S1 still keep the G3 designated port discard all user traffic. So this is root protection. Root protection you only apply on will have effect on designated port. So for S3, let me change the priority back to 32768. Okay. Then what happened? Designated port should become forwarding again. Let's see. That's great. So here you can check. Okay, 106 STP. Okay, that's all for STP. In the event that the root bridge temporarily fail in the STP network, the next viable switch will take over as a root bridge. What will occur once the failed root bridge once again become active in the network? So if the previous root bridge is down, they will elect a new root bridge. When the root bridge or the previous root bridge is become active again, so means that the previous root bridge will run the elections, take over the decision or become the root bridge again. So this situation we call this is preemptions. Something happen in the network will straight away affect the whole network. So that's why you can see once I should change the STP priority. Okay, so they will straight have a topology change. Because so this we call preemptions. And what is the difference between path calls and root path calls? So the root path calls we mean is the total cost, the lowest total cost for the switch to go back to the roots. And path cost means the cost for each port. That's all for each port. So it means the root path cost is the sum of path costs, many path costs. Let's see, check again. Display STP brief, yes. Designated ports, forwarding. Okay, so you go back to forwarding state. Okay, So that's, I think that's all for this SDP. Let's see what else maybe I missed up. No, so that's all for SDP. Then we're going to RSTP. RSTP is a very short one because they still works the same, just they added a new mechanism to speed up the election process. So there's no more election process. We call the new mechanism, we call it proposal and agreement. Okay, proposal and agreement immediate negotiations. So let's see. So RSTP, Rapid Spanning Tree Protocol. So the original SDP standard was defined in 1998. You can see 1998, for which a number of limitations were discovered. Okay, particularly in the time needed for converge to occur. So in all of this, RSTP was introduced. So the fundamental characteristics of RSTP are understood to follow the basis of SDP. So because SDP, RSTP, they still works the same. So in this section, in this topic, we just try to emphasize what is the difference, the core difference of between SDP and RSTP. So again, we try to see what is okay. So SDP weakness, convergence timers, 30 seconds to 50 seconds, at least 30 seconds to 50 seconds. So RSTP don't have this timer. They use the proposal and agreement immediate negotiations. So how they works? So port rows, in terms of port rows, RSTP introduced two new port rows, what we call the backup port and the alternate port. So I know in SDP, I mentioned in SDP we have three ports: designated port, root port, and the alternate port. So this is something that very contradict in the slides, so in the training materials. But just bear with me. It does need, because in the, let's say, if you do access to the Huawei HCIA, the product documentations, in SDP, they don't really mention anything about alternate port. They just mention about designated ports, root port, and block ports. So block port. They only in RSTP, they only mention two port is being introduced, which is this one, backup ports and the alternate ports. So when inside the exam, what we try to answer is backup port and alternate ports. This is your answer in the exam. Okay, these are the two new ports introduced in RSTP. Okay, so alternate port is the alternate path to the root bridge, or you can say it's the alternate for a root port. Backup port is a backup for designated port. Okay, that's why you can see this root port. Beside the root port, there's alternate ports. Root port, alternate ports. And then beside the designated port, there's a backup ports. But when you will see backup port is when you are using a hub. When there's a hub. What happened here is, you still remember what hub do is, it was whatever the hub receiver, he will broadcast. So means that for this switch, he send the configuration BPDU, or in RSTP we call it RST BPDU. Okay, and then this port also send. Means that when the okay, I use a different color. Send BPDU, the hub will broadcast back to the switch himself. And then in this direction, the switch also send the BPDU, the hub also broadcast back to himself. So means that means that the switch receive his own PPDU. So the switch will know that, oh, maybe, so this one of it will be the designated port, another one will be the backup ports, because they are connecting to the same segment, same network. Okay, so how to compare? It's based on the port ID, or to say the port numbers, because both sides, you send to himself, you send back. Both sides, because in both the root part calls in both BPDU will be the same, because sent out by the same switch. And then you compare the bridge ID, the bridge ID on the both sides. You compare the bridge ID, also the same, because sent by the same switch. So therefore you can next you have to compare the port ID. So port ID, you compare the port number, because the port priority will be the same if it follow default. So you compare the port ID. The ports with the lower port number will become the designated port. The port with the higher port number will become the backup port. So you will see backup port when there is a hub. Other than hub, you will never see this backup port. So there's another ports. You can say this is a H port. Is another kind of port, but this is actually this is what we name. So listen to my statement. All the designated port. So you can look at this. You can see S3 G4 is connected to PC2, means the end device. What port is this? SDP brief G4 designated port forwarding state. Okay, so all the designated ports connected to the end devices, we also call that an H port. So H port is a port that doesn't participate in elections, the root elections. So H ports do not need to receive PPDU. Of course, because it doesn't need to join the elections, and it can instantly forward data. So when there's any device connected to the ports, to the H ports, the H port will straight go from start with blocking state. You'll never wait. No need to wait 20 seconds, 15 seconds, 15 seconds. No wait. Just straight jump to forwarding states. So this is the configuration is being done in the enterprise, in the live network, because this is a very good command, very good configurations. This is to also have to speed up your SDP converged network. Okay, so later we also learn how to configure H port. So port state of ICP. In SDP you have 5 states: disable, blocking, listening, learning, forwarding. RSTP, all these change to discarding. Why? Because this is disable means not forwarding user traffic, so we discard all user traffic. Blocking state also discard all user traffic. Listening also discard all user traffic. Don't care anything. Don't even learning. Don't care. But in learning state, we still remain learning state, because this is now we receive the switch will receive the frame from all the end devices, the hosts, and then they will learn the MAC addresses. But it's still not forwarding user traffic. But still 15 seconds. After 15 seconds, go to forwarding state. Okay, so all the alternate port and backup port final state is discarding. For root and designated is forwarding, same as the SDP. So this is the RST PDU. Looks like everything still remain here. Remain. Same. This one is changed. This one is also changed. And then the flag, I haven't mentioned the flag here is changed. STP only has TCA and TC, 2 bits. But in RSTP-BPDU, we have 1, 2, 3, 4, 5, 6 more bits, total 8 bits. So right here, the most important thing is this: proposal and agreement bit. So this is how the switch running RSTP do the you can say the proposal and agreement immediate negotiation. There's no more something called election. Okay. So, and then designated switch means the switch in SDP concept. All the switch have a designated port. They will be called the designated switch. Generate their own BPDU at hello time, regardless of whether an RST BPDU has been received. So in SDP, all the downstream switch, if in SDP, where only when switch B receive a BPDU from the root, then only he will send another BPDU. But this is different in RSTP. The switch B don't care. Even though I don't receive anything from the switch A, I still keep on sending my BPDU, RST BPDU every 2 seconds. So this is different. So you have to remember converge. So this is how the RSTP converge. All RSTP enabled switches began as a root. Same as the STP, everyone thought that themselves is a root because they don't know each other, the existence of each other yet. So they taught themselves, all the switch assume themselves as a root and send RST BPDU. Okay, with the proposal bit set to 1. They propose to each other, I am the root. So all ports are set to a designated row and discarding state. Designated row is to send so that they can start to send. The only designated port row can send RST BPDU, and then they need to be the discarding state. This is meant by discard all user traffic, but not the RSTP BPDU. Okay. Next, so let's say, take example, the negotiation between A and B. So there's exchange, RSTP-BPDU, then switch B will know that switch A is the root. Where it's more suitable become the root, higher priority to become the root. So, so switch B will reply with a RSTP-BPDU with the agreement set to 1. And proposal 0 because SP want to agree A, tell A, I agree you are the roots, and I change to myself this port to root port. So again, switch A receive the switch A receive the RST BPDU for switch B, know that I am better. Switch A will know he's better. I am better, and I am the roots. So switch A keep on sending RST BPDU every 2 seconds. Tell switch B, I am the root, I am the root. So this is what happened between A and B. At the same time, also the same thing also happened between A and C. Okay, next. So when in the process of the negotiation between A and B, B will block the ports. Block all the other ports. If there's other port connected, block. For switch also block the port, block all other ports. Okay, because they want to do negotiation with switch A. So only after the port row is decided, okay, decided already, they will unblock the other ports. Let's say after unblock the ports, okay, so after unblock the ports, it's time to negotiate between B and C. So how they decide is still same as BPDU, same as the STP, same STP. So B and C compare the root path cost is the same. Okay, 20,000 20,000, and then we need to compare the bridge ID 32768, 32768. Cannot. So compare MAC address. This is 42. This is 43. So B is better. So this is designated port. This will be turned into alternate port. Okay. So it is same goes to the port ID when you have two link direct connected to a switch. Even though you direct connect, not necessarily must direct connect to the root bridge. Even two link connected to a non-root switch also have to compare the port ID. So in RSTP, when there's a root failure, a link failure, what happens? Also the same, run the proposal and agreement negotiation to select the new route. Okay. Okay. So what about this is the root failure. What about the link failure? Okay, this doesn't mention. So if one port is down, so how long is or maybe there's no port is down. Does that? How long the switch B will wait? If the switch B doesn't receive the BPDU from the roots before he assumes the root is dead, the root is died. He wait for 3 hello time means 6 seconds. 3 hello timer 6 seconds. Then after if switch B doesn't receive the BPDU, the RST BPDU from the root for 6 seconds, switch B assume the root is died. So he will start the proposal and agreement negotiation with switch C with other switches to run to select the new routes. So in STP is 20 seconds. In RSTP is 6 seconds. So it's faster. So topology change process. So if something happens, switch C, let's say something topology change. Topology change. Switch C will send the RST BPDU. Okay, topology change, bit set to 1, then send to switch B, send out for the reports. Send to switch B. Switch B will flush his MAC address table for all entries in MAC address table except the entry he learned at the port that he received the RST BPDU. Means flush. Then send the RST BPDU to switch A. Switch A also you receive at this port. I flush all the MAC address entry I learned at the other ports. Everything. So you don't even need to wait for 15 seconds. Okay. So STP interoperation is just to tell you if this switch run RSTP, this switch run RSTP, but this switch run STP, what happened? It can backward compatible. So between A and B, we run RSTP. Between A and C, STP. Between B and C also, STP, backward compatible. So setting the mode, same, STP mode, RSTP. So you can just do that first. So let's do it. On S1, system view, STP mode, RSTP, enter. So now you already changed the mode. You do it the same thing for S2 and S3. So with the S2, system view, STP space mode, RSTP, enter. S3, STP mode, system view, STP mode, RSTP. Okay. So I look at the Wireshark. Let's see. This is configuration BPDU. That should change to RST BPDU. Let's check how is the RST PDU RST BPDU looks like. The protocol identifier PID is still the same. This is a span entry protocol, but the version is version 2. Okay, it's 2. Means that this is a rapid span entry RST. So BPDU type, this is a rapid, this is RST or MST. RST for RSTP, MST for MSTP. And then the bit, you have 8 bits. Okay, 8 bit. Then there's the agreement and proposal. So all the other things remain the same. Your max age is still 20 seconds by default. Hello time also 2 seconds by default. For delay still 15 seconds by default. Same thing, nothing changed. Other, just with extra 6 bits, and then the version identifier is changed. So how they decide the root bridge and how they decide the port row is still the same. Compare the bridge ID to select the root bridge, and compare the root path cost and then bridge ID or the port ID to decide the port row. Still the same method. Just they do it. RSTP do it faster. Okay, faster convert speed. So set the H port. So how to enable H port? By default, the ports, all the ports are not H port by default, are non-H port by default. So you have to go into the ports. This, when you're doing your configurations, you already confirm. You must confirm that for all these ports, these certain ports, maybe port 1 until port 10. This is a H port. No, this is all the ports that will be connected to the end device. So I can set it to H port. So in the topology in ASP, port G4 of, let's say I use S3. Interface G004, port G4 in S3 is connected to the PC. So here I use the STP, H port, enable, enter. So I display STP interface G004. Then you can see that. Where's my H port? Port H, enable, active, enable. Okay, let's see the next command. So because by default everyone is not H port, so you can configure, go into each port, configure one by one. Also can, you also can configure in the system view. Use the command STP H port by default means you change all the ports of the switch become an H port by default. But we not recommended these methods because you might causing loop. Because if you plug you connect a switch, connect the port, connect the H port to a switch to join the election, it might become go into the forwarding state, so it might causing loops. So this one we recommended configure one by one. It only in the ports that you confirm is connected to the end devices. STP H port enable. So, and then for the H port, you also can provide protections. We call it STP BPDU protections. This protection is only applied. See, this is applied in system view. When you apply this, means all the H port will have this protection. So when all the H port with this protection receive a BPDU, I don't care what is the bridge ID, what is the root path cost, I don't care anything. When the H port with a BPDU protection active, when the port receives the BPDU, it should shut down the ports. Okay, administratively shut down. means that you need the administrator to go manually to undo the shutdown. Undo shutdown the port to bring the port up. So, and this switch also will send an alert to the NMS because something happened, because we don't expect to receive BPDU at H port. Because end devices will never send BPDU. Okay, and then here for alternate ports and for root port and alternate port, we can have a protection. We call it loop protections. So if this CCG1, which is the root port, if BPDU fail to be received by the downstream switch, the root port is blocked to prevent switching loops from occurring. So the purpose of this, so what happened here is the switch C, this is root port, right? Okay, so this after the port, this is blocked. Okay, so somehow the BPDU sent by the root bridge is congested in the traffic congestions. So switch C switch C not able to receive the BPDU from the switch A for 6 seconds. So for 6 seconds, oops. Yeah. So switch C unable to receive the BPDU from the root for 6 seconds, but the link is still up. The link is still up. Just the BPDU is congested, stuck somewhere. But the switch C will thought that maybe the root is already died from this direction. Okay, from this direction, the root already died. So you have to select a new root, right? Select a new root. No, maybe I should change this to designated port. Okay, this is my new root port. Okay, because you still can receive the BPDU from this direction, but not from this direction. What he do is he change this to designated port. This to root port, because this is because I cannot receive the BPDU from here, but I receive from here. Means that this become the only way, only port I can receive BPDU. I can go back to my root bridge. So this become the root port. This become the designated port because the link is still active. The traffic is still going, but I don't receive any BPDU. So I try to send BPDU. Send BPDU. So if nobody is replying, so this port will eventually become what? It will become forwarding state. Forwarding state. These are final state also become forwarding state. Then you will see you form a loop. Form a loop. So to prevent this, is on all your root port and alternate port, you can apply loop SDP loop protections. So this is what happened is when all the ports that group port they configure with loop protection not receive BPDU, after 6 seconds he will change to discarding. Okay, change to discarding. Change to discarding state so that this can change to root ports, change to designated port, discarding state, but so that this link is down, this link is up. So no loop is happened, no loop. Okay, and when somehow the BPDU managed to reach the switch C will change back this back to root port, this back to alternate port. It's very preemption. All the actions, maybe something happened, you should affect the SDP network, the whole network will be affected. So next one, you can see configure validation, you can see the protection type loop. you have. Okay, so what is the purpose of the sync that occur during the RSTP proposal and agreement process? The sync process. This is what I mean by this. This is a sync process. This, upon receiving a superior BPDO, switch B will cease to send RST BPDO containing proposals and beginning to synchronize. So, purpose of the sync process, under the sync process, the switch will block all other ports. All other ports is to prevent the loop, prevent loop, because it block everything, so you can confirm everything is discarding, so no loop. So because between the switch A and B, the negotiation is very fast. How? You send one BPDU, then send the next one. Done. Configuration is done. Just for 4 seconds. 4 seconds is done. Configurations. So we try this HPOT. Already configured. Display this STP HPOT enable. So display STP brief. Now G4 is designated port forwarding state. So what I demonstrate is I try to stop the port, stop the PC. Port is down. Then I start. After I start, I should go to display STP brief. The G4 should go into forwarding state. So the PC2 can start to send data. Start to port. The port actually is the port. G4 can start to forward user traffic.
Downside. Yes, now candidate.
Okay, so I think that's all for this RSTP. Okay. Okay, so that's all for this RSTP.
Hello, Mr. Bell.
Yes.
Please, can we have port state transition for RSTP2?
Port state transition for RSTP. Okay. Port state, the port state in RSTP only have 3 states. Okay, let me show you again. Then okay, only 3 states. Okay, only 3 states. So what is the periods? Okay, what is the period? So for discarding state, go to learning state. How much time? For at least 4 seconds. What I mean by this is when everything, all the switch start discarding state. That's in the port discarding state, they send each other. One BPU, BPDU. Means that for in terms of one switch, let's say one switch, the switch send one BPDU, RST BPDU. First one send. Then at the same time, the other side also send. So you receive. Then you decide, oh, if I am the, I will become the root ports. So you will send another one after 2 seconds. So you send, then you already changed to root ports. I change to root port, it should go into learning state. This is still 15 seconds learning.
So from discarding to learning.
Or discarding to learning is very fast. You can say it's 2 seconds actually.
Okay.
2 seconds. I send the first one. And then 1 second, 2 seconds. I send the second one. Done. Change to learning. You can say it's 2 seconds. So, but this transition is very, you can say it's very fast. Okay. Very fast.
So the convergence time for RSTP is, let's say, 17 seconds?
Yes, you can say that. Less than 17 seconds.
Thank you.
Okay. Okay, so for now, now it's already 10:48. So we try to we can take a break. After we come back from the break, I will give some quiz and then some questions to test your knowledge. Or you can use the question to try to recap to strengthen your concept and knowledge in this STP and RSTP.
Okay, thank you very much.
Okay. So let's continue at make it straight 11 a.m.
The figure shows a simple network. It consists of two layer 2 switches, a PC, and a server. If a single point of failure occurs, the whole network is disconnected. Such a network is not robust and lacks redundancy. To enhance network redundancy, the following network architecture is selected. This network architecture, however, introduces loops. To prevent loops, a time to live field is added to the IP packet header of a layer 3 data packet. The TTL decreases by 1 each time the packet passes through a router. If the TTL decreases to 0 on a router, the router discards the data packet and replies with an ICMP TTL timeout message to the source. The TTL helps in the figure consists of 3 switches. This is a typical layer 2 loop. Data frames are transmitted within the layer 2 loop and layer 2 switches transparently. The TTL helps prevent the packet from being looped. The loop shown in the figure consists of 3 switches. This is a typical layer 2 loop. Data frame 2 switches transparently transmit them. In this situation, using a TTL field cannot prevent a loop. Loops can result in a variety of problems, such as broadcast storms. When a switch receives a data frame, the switch performs the following. Obtains the source and destination MAC addresses in the frame header. Learns the source MAC address. Adds the source MAC address into the MAC address table. Generates a mapping between the MAC address and the port that receives the frame. Searches in the MAC address table for a port matching the destination MAC address and forwards the frame through a matching port. If no match is found, the switch floods the frame to all ports on the network, except for the port that receives the data frame. SW3 receives a data frame sent by the PC. If SW3 finds no entry matching the MAC address, or receives a broadcast frame with an all F's destination MAC address, SW3 replicates the data frame and broadcasts the frame through all the other ports. Upon receipt of
Hello. Mr. Bear.
Yes.
Sorry, I believe I've missed so much, right?
Sorry, again?
I say I must have missed a lot, right?
Miss a lot. Not really a lot. Just some concept. Do you still remember what you learned yesterday?
On which one? STP? RSTP?
STP, yesterday.
Yeah, STP, of course.
Okay. Then what you learned yesterday is much more important.
Okay, okay.
Later I'll test you. So what we
Yeah.
learned today just now, we can do recap by questions. Later we do the questions, then you will know what you need to know. Okay.
Okay.
But the concept I explained yesterday is the most important.
Okay, okay.
Okay.
So where are we now? Sorry.
I will give you some quiz that we will do together. Waiting. Okay.
Okay.
Yeah, give me some more time. Okay. Okay. This one. Everybody can see this, huh?
Waalaikum salam, sai na gajiya. Lafiya kalau alhamdulillah. Wallahi in MTN din yana recharging bai shiga ba wannan layin data.
MK, mute your mic.
Mr. Bear, please able to mute the guy's mic, please.
Okay. Okay. So can you tell me how the STP network is formed from here? Okay. So the first step, I want you to find it. Which switch is the root bridge?
That's one.
Why?
Because the one with the lowest ID.
Priority.
Yes, bridge ID, and more accurate is the lowest bridge priority. Correct. Okay. So this will be the root. Okay. Okay, next step. I want you to identify the port rows. Designated port, root port, and alternate port. So we start with S1. Start S1.
S1, the two are designated.
2 ports are designated port. Correct. Designated port. Okay. So then we'll go to S2.
S2. S2, two is
S2
alternate.
port 2 is
2 is alternate. 1 is designated.
again. What is
Two
this?
is root port.
What is this?
Sorry,
This is-
one is root port.
One
Sorry, again. S2 port 2 is
Port
S2 port 2 is root port.
is
root port. Correct.
Root port, yes, root port.
the root port.
S3
root port.
port 1 is root port 2.
S3 port 1 is also root port.
Root port, yeah.
Yeah.
Okay. What about
That's
S2?
designated root.
S2 port 1 or S3 port 2? Let's start with S2 port 1. S2 port 1. What is this?
S2 port 1 is designated.
Designated.
Port 2 is
Main. Which one?
so
S2. S3.
S3.
S3 port. S3 port 2 is
Is 2 is designated.
No, it should be alternate port.
Alternate port. Sorry, we already have a root port.
Yeah, root port and designated port. It should be alternate port or backup port.
Because S41 is a root port, right?
S41 is a root port. Okay, never mind. We hold on for these two.
2 should be alternate for S3.
X42, if S41 is root port, S42 is designated, then X21 should be backup port, disabled port. S21.
Hold on. Root port S2.
Okay, never mind. All the remaining bits DR on S1 designated correct. S2 port 2 root port correct. S3 port 1 root port correct. So for this and this might be a bit don't know how to decide. Never mind. We can go to S4. S4. So when deciding the port rows, for all the non-root switch, because for root switch you know that designated, that's always designated. For all the other switch, the first port you should start with is the root port. You find the root port first. Okay, because there is only one root port for each switch. Then the other you can decide later. So let's see. Go for S2, S4. S4. Which one is a root port of S4?
The root port of S4, it should be 1.
Okay. So root port for S4 should be 1.
1.
Why?
Because lower port ID.
No.
Lower bridge ID.
No.
Why? In terms of why do you say that?
We have 1 and 2.
It doesn't related with the port number, no.
Okay, so the 1 and 2 is not representing low and high, is it? It's just the number of
No,
ports.
it's just a port number. Yeah.
Or if the port number, one is lower than the other, isn't it?
Yeah. This port number is 1. This port number is 2. Yeah.
Yeah.
This is the label.
On S-
This is correct. But why this is root port? It
Because you can't
doesn't.
have, hello, Mr. Bay.
Yes.
You can't have 2 root ports on S3.
Yes, of course, you can't have two root ports.
So 2
But
on
because
S3.
now I want you to look for the root port of S4. Which one? 1 or 2? And you say it's 1. But why? 1 is correct. It's 1, but why?
Because on S3, port 2 will be alternate.
Because on
Yeah,
S3 has the lower bridge priority number.
Okay, before you compare the port ID, what should you compare first? First one, you should compare the root path cost.
Okay, the root path cost.
Follow the sequence. First one is root path cost. Second one, if root path cost cannot decide, then only you compare bridge ID. If bridge ID also cannot decide, then only you compare the port ID.
Okay. Let's look at that. The root path cost for S2 to S4 is 20,000, is it?
S2 to S4 mean so
20,000.
what's the root path cost sending out from the root?
0.
Is 0.
0.
So for S2 to go back to the root is 0 plus this one. If this
yes, plus 2,000.
Yes, 20,000. Let's say all the ports are G port, 20,000.
Yes.
So 40,000. For this, send out also 0.
0.
So 0 plus this, 20,000.
20,000.
Okay. So S3 will tell S4. S2 also will tell S4. What is mine?
Yeah. So that will be 40,000.
20,000. Right. And then S4 at this spot and this spot. So at here, 20,000 plus 20,000, 40,000.
40,000.
Here also 40,000. Here also 40,000. Right? So which one is lowest? 1 or 2?
In this case, they are the same.
They are the same. Oh, cannot decide. So move on. We compare the bridge ID.
So we look at the bridge ID to decide now.
Yes, bridge ID of the BPDU sent out from S3 and S2. Bridge ID of the BPDU. So how you compare? Means that you compare the bridge ID of S2 and S3. So
yeah, so that of S3 is lower.
Again, S3 is lower. All right. 4096, 32768. This is lower. Okay, so that's why this is root port.
Okay.
So this is root port. And then this one is, what is it? This is designated port.
Yep.
Why? You compare the root port cost?
Yes.
Yes. S3 is 20,000. S4 is 40,000. Same as between S2 and S4. S2 is 20,000. S4 is 40,000.
Yes.
So left one. This one is
designated.
Again. Sorry. This one is. What is this one?
1.
This one is what port? Is this?
No.
It's alternate port.
Yes.
Alternate port, yes. Alternate port.
Okay. So you totally can understand this one.
Yeah, it makes sense.
Yeah. So this one. Let's see. Let me post somewhere. Okay, so I share the picture in the group so you can save it for future reference. Okay, let's see. Okay, never mind. Later we just continue again. Now we just to do some questions. Okay. Switch. Okay, so this question will include the switch, okay, the single switch topic, and then STP and also RSTP. So let's try to answer together. So start with the first questions. A layer 2 LAN switch generate MAC address table entries according to the receive frame. To what? Select one answer.
According to the source MAC address.
Source MAC address.
Source MAC address. Correct. Next one. Which of the following information is not included in the MAC address table of a switch?
The IP address.
The IP address is not included. Correct. Oops. Okay, so which of the following statement is true about the MAC address table of a switch? So which ABCD, which one is true? Select one answer. Display MAC address, so this is the what you see. So going one by one, the answer. When the slave port receives a data frame, slave port means all the ports just mean the ports. Don't need to care about that. What is a slave? It's just a port. Switch port I can treat that. So a data frame whose source MAC address is 5489.9885.1888. This one. And destination MAC address is 5489.989D1D30.
Yeah, it's a forward.
The switch forward the data frame through E1.
It's a forward through E1.
Is it correct?
I thought the listening port is the alternative. Okay. Hello?
Hello? Yes?
I thought it can only forward through the destination, the destination.
Destination MAC address, 1D30. 1D30 is E1. Is it correct? Yes.
Correct.
Is it? Or let us check again. Check the other answer. When the switch restart, the MAC address learned by E3 need to be learned again. learned by E3. Learned by E3.
That's
Is it
false.
gone? False. Because it's
No,
static.
it's static.
It's static.
Okay. So this statement is false. Next one. When the switch restarts, the MAC addresses learned by E2 do not need to be learned again. Switch
It's already on the
restarted
map.
E2.
It's already on the map table.
That's incorrect.
That's incorrect because this is dynamic. If you restart the switch, this will be flushed away.
Yeah, it will be flushed.
Yeah.
Okay, so this statement also false. Next one. When the slave port receives the data frame whose source MAC address is 5489.9811 0B49 and destination MAC address is 5489.99D 1D30, the switch forwards the data frame through E2.
So,
E2.
can you shift it up a little bit? We can't see the last option. Oh, okay, okay. Uh-huh.
So it's just a contradict with the A and D. Either choose either one only. E1 or E2? Of course, it's E1.
That looks like a false statement, D.
Yeah, so false statement. That's why. Yes, select one answer only. So this is confirmed. This is a correct. This is a true statement. Okay. Next. So in the exam, there will be a lot of this kind of questions. So you'll be careful with the port number, the ports, and the MAC address, and the actions it takes. The switch takes. Be careful with this. So next one, after a switch receives a unicast data frame, it searches the MAC address table for the destination MAC address. Which one of the following statement is false? Select one. Which one is false? Look at the first one. If the MAC address is found and the port corresponding to the MAC address in the address table is a port through which the switch receives the frame, the switch discard the frame. Is this true or false statement?
As false.
Again, is this a false statement?
Yeah.
Why?
Because you do not discard it since it knows it acknowledges the MAC address.
Yeah. If the MAC address is found on the port corresponding to the MAC address in the MAC address table, is the port through which the switch receives the frame. The switch discard the frame. The switch receives a unicast.
Unicast.
Unicast frame. Okay, it's found.
Option A would indicate that probably the address has changed, but the switch has not updated the MAC address table.
Yeah, they are training. They are.
You see, it search the MAC address table for the destination MAC address. Okay.
Okay, it cannot receive and forward in the same port.
It cannot send the frame back to the same port it received the frame.
Yeah. Yeah, so it's true, right?
No.
Okay, let's see again. If the MAC address is found, okay, the destination MAC address is found and the port corresponding to the MAC address in the MAC address table is the port through which the switch receives the frame. The switch is discard. The switch discard the frame. Yes, this is a true statement. So this is a true statement. True statement, because according to the MAC address table, the switch need to send the frame back to the same port it received the frame. So the switch cannot do that, so it is discard. So this is not the answer because we're looking for false statement. So next one, if the MAC address is found and the port corresponding to the MAC address in the MAC address table is not the port through which the switch receives the frame, the switch forward the frame. Okay.
Yes.
True.
This is a true statement.
True. This is a true statement, yes. So next
G
one.
is no.
C, if the MAC address
C is
cannot be
false.
found, the switch discard the frame.
Yeah.
False.
False. Because if the MAC address
Yeah.
cannot be found, the switch blurs the frame.
What's the frame? Yes.
So this is a false statement. This is the answer we're looking for. False
Not the
statement.
frame, yeah.
Okay, next one. Layer 2 switch are data link layer device that identify MAC addresses of layer 2 data frames and forward layer 2 data frames based on MAC addresses. In addition, they record mappings between MAC address and the interface in the MAC address table. True or false?
True.
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 Okay. Which of the following technologies is used to bind MAC addresses to interface on a switch? Which one? ACL, port security, NET, or SCP?
To bind mark.
So I never mentioned this
Is
for
it not
in
NAT?
the. No, NAT is for layer 3.
Layer 3, okay. ACL
Is
then?
ACL? No.
No, that's access.
What is
now.
SCP?
SCP.
It's port security.
Yes, the answer is
Port security.
the answer is port security actually.
Port security. Yeah.
Wow. I have no idea on that.
Yeah. So this is what they didn't mention in the training material. I also never mentioned. So port security is in IP level, the professional level.
Okay.
Okay. It's one of the technology, but still you can configure static. Okay, static in the MAC address table. You can configure static, or you can use the technology called port security.
Okay.
So next one, which layer of the OSI reference model does a switch work at?
Data link.
Data link layer. Correct. Okay, that's a diagram. As shown in the figure, assume that the MAC address table for switch A is as follows. This is the MAC address table for switch A. Host A send a data. This host A send a data frame whose destination MAC address is MAC B to switch A. Which of the following statements is true? Select one.
Data frame.
Switch A forwards the data frame. The data frame. Only true. G3 is wrong.
False.
False. Switch A floods the data frame.
False.
False. Switch A forwards the data frame. Only true. G2.
True.
True. Okay, so the switch discard the data frame. No. Okay. That's one. So this is smaller. Okay, as shown in the information not preceding the next information when the switch needs to forward the frame whose destination MAC address is 549.98 EC F011. Which of the following statements is true? So the destination MAC address of the frame is 98 EC F011, not 18. It's 11. What happened? The switch needs to send a request to discover the device whose MAC address is 549.98 EC F011.
It's dynamic, isn't it?
It's dynamic. This is F018, not 11.
Yes, they have to flood.
Is this sending an ARP request?
You know, bring water concept.
Is this Only select one answer. Select the true statement.
To send a request.
I don't know how to buy water. You know, so water.
Or you look at the second, look at the B. The switch flood the frame to all ports except the port through which the frame is received.
Correct.
Yes.
Oh, this is right. So means the A is wrong.
Yeah.
Is it only one answer?
Yes.
Okay. So
the switch need to send a request to discover the device whose MAC address is this. This is done by the host send ARP request, not the switch.
Yes.
I never tell you the switch will send the ARP request. No. Okay.
I didn't get
so, so if the switch doesn't find any entry matching, so discard is also wrong.
Okay.
Okay.
Oh, no problem.
Okay.
Time.
Next. So 10.
I've downloaded the videos. I told you I'm arranging them. I finished.
Which of the following statements?
Your mic.
Okay. So which of the following statements are true about the static MAC address table? Static. Select one or more answer. After a device is reset, an interface card is hot swap, or an interface card is reset, the safe entry on the device or the interface card are not lost.
After it is reset or swapped.
The entry is not lost.
It's the static entry.
The static entry.
It remains.
It remains. So I mean this is true. Not lost. It remains. So next one, each static MAC address entry can be bound only to one outbound interface.
Each MAC address outbound interface. That looks true.
True. Either is dynamic or is static. One MAC address only can bound to one interface in the MAC address table. You can check whether data is forwarded between two connected devices by checking the static MAC address entries.
And it looked true also.
Whether data is forwarded between two
connected devices by checking the static.
The type does not determine.
Okay, so can I check? Is because if when for the switch, let's say a switch, when there are some frames sent by host, sent by devices, when the switch receive, then he will learn. Means there's a data forwarding, correct?
Yes.
Can we check? But can we check is there any data forwarding between two devices by checking the static table? No, because even there is no data forwarding between the device, with the static is still there.
Yeah.
Okay, so this is false. So after an interface is statically bound to a MAC address, other interface discard the packet whose source MAC address is the bound MAC address. Okay, again, after an interface is statically bound to a MAC address, a static MAC. Okay, after other interfaces discarded a packet whose source MAC address is the bound MAC address.
Other interfaces of a different switch or on the same switch?
Same switch.
No, it's false.
You mean this is a false statement?
Yeah. Why would they discard it if just because it's statically bound?
Let's say this interface is statically bound to a MAC address, or you should mean the MAC address bound to an interface. Let's say MAC address, let's say MAC address AA is bound to G1. Okay, the other interface, such as G2, discarded packets whose source MAC address is AA.
Okay.
It's false.
You can't have
It's
the
false.
same. The interface cannot have the same MAC.
What that thing is trying to do is trying to let you know that it means from this interface you cannot send packets to other interfaces.
This is
but are they blocked?
What is this?
But that thing, I don't think it's correct.
Mr. Bay, I think you need to explain this answer you're choosing.
But it's not correct. What you have just done is wrong.
Mr. B.
Yes.
I'm a little confused about D. I mean, if you're bound, one of them are static and the rest are not
dynamic,
are not static, they're not supposed to discard.
Why would they be discarding packets?
Exactly.
Because of this. So remember this one? Now, AA 0, 1, 2, 3 AA is static, bound to G1. Now, G2 receive a frame which the source MAC address is AA.
G2.
Now this frame is coming in at G2. Now the switch look at the switch, check the source MAC address is AA. Then I check AA, G1, but this is static, means that the switch expected that any frame with source MAC address AA should be coming in from G1. But it's static. Static means you cannot update.
Oh, okay. I see.
So draw, discard.
So you're saying that it's only all packets are only expected from G1 if it's AA. So any other one that is not bound to.
I means that all the source MAC address with all the frame with source MAC address AA should come in at G1. Yes.
Okay.
If the switch see this frame coming from all other ports, discard.
It's okay, makes sense.
Okay.
Okay. So back to the question.
This is what it mean.
It's true.
Yes, this is a true statement.
Wait, after this, okay. No, I don't agree. It's not the same as the question. Sorry.
It's the same. It's actually exactly the same as in the slides.
No, sorry. This statement says after an interface is statistically bound to a MAC address, that is AA to G1, other interfaces discarded a packet whose source address is bound to the MAC address.
It's the bound. It's the bound MAC address.
Yes, so that means that other interfaces discarded a packet whose source address is AA. They have no reason to discard packets from AA just because AA is bound to G1, because that's what this statement is signifying. It said after AA is bound to G1.
You agree with this?
Yeah, this is fine.
Sorry. Now using this diagram, right? We're saying AA is bound to G1.
Yeah.
Yes.
And then we're now saying that BB is dropping the packet because it is coming from G1 or from A. That's what that statement is saying.
Hello, Mr. B.
See, all other interface, drop the packets whose source MAC address is the bound MAC address.
Excuse me, Mr. B.
Yes.
So what you're saying is that anything, in simple terms, that packet is expected only if its source mark is bound statically. That packet is expected through a particular port only.
Yes, it's expected to
saying?
coming in at G1 only.
Okay.
Yes, but the statement is saying that G2, G3, G4 are dropping the packets only because it is coming from G1.
No, because the source mark is bound to G1.
The source mark is bound to G1, yes.
Yes.
It's just
So
like saying, myself and Bay are connected, and then you would not be able to receive messages from me because myself and Bay are connected. That's what that statement is saying. It is outside of what this diagram is saying. There are two different scenarios.
No, the way I understand it, if the whole thing is flooded, then anyone that sees a statically bound mark whose source is supposed to be only through G1, it's not their own. So they discard it.
It is not for them. The source, it didn't say the destination, it said the source.
Yeah.
Yeah,
the
source.
Says the source.
Yeah.
So if the source is from AA, if the source is from AA through G1, why would G2 drop it? That's my question.
No, because if it's flooded.
Now the situation in this is the frame. I don't know, somehow a frame with source MAC address AA is coming in at G2. So what G2 will do is discard this
Of
frame.
course, yes, if it comes from another, but this one, it is coming from G1. From that statement in the question, it is coming from G1.
Let's look at the statement again, Mr.
After an interface is statically bound to the MAC address, that is AA is bound to G1.
Yes.
It now says other interfaces discarded a packet whose source MAC address is bound to the MAC address.
Yeah.
Right. Yes.
So if AA is bound to G1, if AA is bound to G1 as a source, why is G2 refusing the packet because AA is bound to G1? Why does G2 refuse the packet as a destination?
Mr. Bay.
Yes.
I think based on your statement here, right? Based on your statement here.
The argument went enough only one question one day. So, sorry, don't
Mr. Bay, can I speak?
Yes, sure.
What I'm saying is that based on that picture, the packet whose source mark was bound to G1, actually the packet came through G2, right?
Yes.
Yes.
So G2 was not expecting a packet whose source mark was bound statically because it was meant for G2, it was meant for G1.
Yes.
Yes.
I think that's just it.
But the statement says differently to my understanding, but then again, we could move on.
Yeah. For mine, this is the true statement also. Okay. You can. Okay, let's move on. Okay, which of the following statements are true about the dynamic MAC address table? After the device is reset, an interface card is hot swapped. When an interface card is reset, the safe entry on the device or interface card are not lost.
A is false.
False. Okay, not the answer. So dynamic MAC address entries are obtained by learning the source MAC addresses of packets received by an interface and can be hashed out. Is this true?
Oh no, let me see that again.
Dynamic MAC address entry are obtained by learning the source MAC address of packets received by an interface and can be hashed out. Means can be typed out. True.
Yeah.
Yeah, it can be hashed out.
Yes, because it's dynamic. So C, after a device is reset, an interface card is hot swapped or an interface card is reset, dynamic MAC address entry on the device or interface card are lost.
Yes, it's flooded.
It is true. You can obtain the number of users communicating on an interface by checking the number of specified dynamic MAC address entry.
Yeah.
Yes. Okay, because only when there's a data forwarding between the user, then only they will have dynamic MAC address. Okay, next one. As shown in the figure, all hosts can communicate with each other. Which of the following statements are true? So select one or more. G3 of S switch 8 learn one MAC address. G3 of switch 8 learn one MAC address. Is this correct?
Yeah.
Yeah. You learn the MAC address of host C.
Okay.
Okay. G3 of switch B learns two MAC address. G3 of switch B learns two MAC address. Is it true?
Sorry, go back to A again.
G3 of switch A learns one MAC address.
But there are two hosts there.
Yeah. The two hosts is here.
Why is it not learning from the MAC of B?
Because the switch A learned the MAC address of B at G2.
Yeah.
Switch A learned the MAC address of A at G1. Now I'm looking for G3.
What is happening here?
Host C, okay, this is host C coming in. The phrase coming in. Switch B check the MAC address, source MAC address coming host C is MAC C. So means that in the MAC address of switch B is MAC C is
true.
G1. Come to here.
Okay.
The same frame come to switch A. So switch A check the MAC address, check the source MAC address is called MAC C. So MAC C is MAC to learn at G3, correct or not? So G3 of switch A learns one MAC address. Because the other two is learn at G1, G2.
Okay.
So A is correct.
Right. Yeah, from host C. Yeah, that makes sense.
Yes.
After this question, I have a question to ask.
Okay. How about this? G3 or switch B learns two MAC address.
Yeah.
Correct, huh?
True,
yes.
true.
Learn the A and B.
Yes.
A and B.
Yeah.
Correct. Okay. So what is the questions you want to ask just now?
Switches have MAC addresses, right?
Switch have MAC address, yes.
Okay.
Okay.
In light of the question we just treated, switches have MAC addresses, I'll just say.
Okay. Switch have MAC
You
address.
understand what I mean? Yes.
Yes. Switch
So in light of all switches have MAC addresses, right?
Yes, correct. All switch,
So
all
in
network
light of the
device have
question-
MAC address.
So in light of the question we just treated, in practical terms, the question itself will be wrong.
Again?
Because switch A should be learning the MAC address of switch B.
The host is learning
and
from the host.
A.
Why the switch A will learn the MAC address of switch B?
Pardon?
Because it's connected on its interface.
It's just connected. Why is want to learn?
I'm just saying because the question does not indicate that switches have a MAC address. That was the point of my question.
Excuse me, Mr. Bay.
Yes.
Are we saying that are the switches not learning the MAC addresses of their host?
Yes, the switch learn the MAC address of the host. That's
Which
what
means
what Michael says. The switch A also should learn the MAC address of switch B.
the host MAC address. I mean the MAC address of the host of switch B.
No, the switch itself.
The switch itself, the switch B also, all switches, all network devices have MAC address.
Yes.
Okay.
So which of the MAC are we learning?
Michael, what Michael means is the switch B also have a MAC address. Maybe like put a MAC.
Yes.
MAC SS. No, maybe D, E. Also can. Okay.
No, but Mr. Bay,
Yes.
if that's the case, he's right. Because I mean, in this case, A says G3 of switch 1, switch A, learns one MAC address, right?
Yes. Yes.
So the switch B has a MAC, and then the switch B has a host that has a MAC, right?
Yes.
Yes.
Switch
So,
B has a MAC address.
So are we not looking at 2 here, not 1?
Okay.
Yes, but you see,
The
question,
switch
that's why I
A,
said,
the switch A doesn't learn the MAC address of switch B is because the frame, because the switch B himself doesn't send anything to switch A.
Okay.
What
okay.
what the frame, all the frames sent by switch B to switch A is the frame generated by host C. The switch B just forwarded it. Nothing is changed.
So in this case, it's only learning the MAC address of the host then.
Yes, you're right.
Okay, sorry. From what you have said, on a standard network where you have 20, 30 switches, the switch, each switch has to learn the MAC address of other switches, basically, right?
No.
Okay.
No. Now we are talking about layer 2, layer 2. Layer
Yes,
2.
layer 2.
Yeah.
Yes.
In layer 2, you will never see the MAC address of other switch in the MAC address table.
MAC address table.
Never.
Really?
Yes, never. Because the switch at layer 2, data link layer, the switch only helps to forward the frame, forward the frame. It doesn't change anything to the frame.
Yeah.
So, so the other switch you'll never see what is the MAC address of the other switch in the frame. Never.
Okay.
Okay. Move to the next one. So, if a device running SDP receives an RSTP configuration BPDU, it discards the BPDU.
False.
It is false.
I think it's false.
It's true.
It's true.
He discussed it
RSTP falls back.
Can I
RSTP falls
understand?
back to STP.
It's discard the RSTP BPDU because it should backward compatible.
Yeah.
The device that send this RSTP BPDU should change backward compatible, change to send STP BPDU.
Okay. Okay.
Okay, next. Okay. Oops. As shown in the figure, all hosts can communicate with each other. Which of the following is true about the mapping relationship between MAC addresses, between the MAC address and ports on switch B? So switch B means we are looking into the MAC address table of switch B. Switch B. So what you will see, the MAC address of A, B, C will be mapped to which ports of the switch B. Which one?
Mark A.
MAC A is now looking at switch B. Switch B.
Switch B, yeah. Mark A, Mark C, Mark B. It looks like C, right?
It looks like C. The answer is C. Yes.
C. It has learned all the mark of the hosts.
Okay, okay.
Okay,
Yeah.
huh? Go from here, go in at G3. Go in at G3. A, B, Mac A, Mac B is G3. Mac A, Mac B, G3. C, Mac C, go in at G1. Mac C, G1, yes. All right. Which of the following protocol can be used at layer 2 network with redundant links to prevent loops?
STP.
STP, very easy. Okay. The root protection functions provided by RSTP can take effect only on designated ports.
Root protection.
Root protection, yes.
I think I missed that part when I was away, but it looks like true, right?
Yes, it's true. Okay.
This is the forwarding port. Yeah.
In RSTP, an H port becomes a common STP port after receiving a configuration BPD.
That's true.
Yes, that's true.
Yeah.
Which of the following parameters are used for STP calculation on switching network running STP? Select one or more.
Port ID.
Port ID.
Bridge ID.
Bridge ID.
Root path cost.
Root path cost. Okay, well done.
Bridge ID. Root path cost.
Yes, correct. Okay, next one. In RSTP, the proposal and agreement mechanism, PA mechanism, requires that links between two switching devices must work in point-to-point full duplex mode.
True.
Full duplex.
Full duplex.
True.
Of course, true. If working half duplex means the two BPDU sent by each other collision. Okay, cannot, huh? Must be full duplex. The loop protection functions provided by RSTP can take effect only on designated ports.
True. Only on designated ports. Loop protection. Yeah, true.
Okay. Root protection. This is true. Hey. Is this true also? This is false. Okay, loop protection only takes effect on root port and alternate port.
Okay.
Okay.
Okay, then which of the following statements is true about the alternate port in RSTP? Which one? Only select one. The alternate port forwards user traffic and learns MAC address.
B.
D. An alternate port acts as a backup of the designated port and provides a backup path from the root bridge to the related network segment. Or an alternate port acts as a backup of the root port and provide an alternate path from the designated bridge to the root bridge. So, alternate port is the backup of designated port or root port, which one? C. So, what port is the backup of a designated port?
The root port.
The backup port. Okay, this is what you miss out. In RCP, we'll have a backup port.
Okay.
A backup port. Okay, let me show you.
Backup designated?
Backup the designated port. This is the questions. refer to the graphic. The switch is operating using STP. All default parameters have been maintained. Okay, which port will be a designated port row? This is a hub. You will see that backup port only when there is a hub.
Okay.
So what happened is when there is a hub, means that switch A send the BPDU. The hub will broadcast the BPDU back to the switch A. The switch A also send a BPDU out from G1. The hub also broadcasts the BPDU back to switch A. Means the switch A receive his own BPDU.
Okay.
So then the switch A notices, oh, one of the port is the designated port because I want to send BPDU. The other port is the backup port. Okay. So, and remember, hub doesn't understand STP.
Yeah.
So whatever answer you can see, E2 or hub, E1 or hub, it can be ignored.
Yeah.
So switch A, either G1 or G2, is the designated port. Which one?
John is in the class. John.
It's hard to determine without the IDs, right?
No, I think we could with the
You
lowest.
still determine using the same sequence. The root pub cost,
So
then the
it's
bridge ID,
0,
then the port ID. Yes, it's G1. G1 port number is the lowest. Because if you compare the root pub cost, same. If you compare the bridge ID, it's the same. Both same by the same switch, but the port number are different. So G1 is the designated port, G2 is the backup port. Okay.
Okay.
Okay. Which of the following description regarding the STP forwarding state is incorrect? Select one. Okay. One incorrect statement, one false statement. A port in the forwarding state can send BPDU.
True.
Is it true? Yes, can send. A port in the forwarding state can forward frame. Yes, okay. A port in the forwarding state can receive BPDU. Yes, okay.
Yes.
A port in the forwarding state does not learn the source MAC address of the frame.
False.
False.
That's false.
Yes, this is false. Okay. On an STP enabled switch, TCA BPDU are sent only when the port on the local switch is faulty.
True.
True, yes, true. During STP calculations, the port cost is associated with port bandwidth. Okay, which of the following statement about the relation between port cost and the port bandwidth is true? So select one. Port cost varies randomly according to port bandwidth. Port cost increase when port bandwidth increase. Or port cost is inconsistent with port bandwidth, or port cost decrease when port bandwidth increase.
D.
Yes. Okay. Users in the network discover that the efficiency of a file transfer is low. The administrator used Wireshark to observe the network and discovered many duplicate frames. Which statements correctly explain the reason for this? Select one answer. The network has not been segmented using VLAN. The network has loops.
The network has loops.
Yes, correct. Okay, next. Okay, so this one. Okay, smaller. Okay, So refer to the graphic, 3-layer 2 switch. 3-layer 2 switch, the center here is a hub. Enable with SDP are connected to the same hub. The configuration bridge ID is as follows, while all the other configuration use default values. Which of the following statements is false? Select one, false statement. Okay, G2 on LSW1 is blocked. G2 on LSW1 is blocked.
It's false.
Why?
There's no indication it's blocked.
No, just you need to determine based on the parameters.
Oh, okay, okay.
Hold on.
Let's see.
Hold on.
32768. 12, 23, 34. Right.
So
So it seems switch one is the root.
Is root, yes.
Okay, switch one is the root. Yes.
Yeah.
Okay, so G2 on LSW1, switch one is blocked.
Yeah, it's true.
Most likely.
It's true.
It's true, huh? Why? Because it is connected to a hub. So this is the hub. So this, but this is blocked because this is the backup port. G1 is the designated port.
To prevent flood loops.
Oops, sorry, we should choose the false statement. A is a true statement.
Oh, yeah, okay.
Okay. Okay.
Which is false? Which is false? Okay. Okay.
Yes.
B is false.
G1 on LSW3 on switch 3 is AP
That's-
ports and is blocked.
That's false. That's false.
G1 or switch 3 is blocked.
On switch 3 is AP port.
Alternate port is that that's mean alternate port.
No.
Are you sure?
Why is it blocked?
Why is it blocked? Because it's a redundant path.
Okay. Right.
Right now, compare between switch 2 and switch 3. Who have the lowest bridge ID?
Switch 2 has lower.
Lower. So switch 2 is designated port.
Yeah.
Switch 3, G1 is alternate port. So this is true.
Blocked. It's true.
Okay. The two interfaces on switch 1 are designated port and are in folding state.
On switch 1?
The two interfaces on switch 1 are designated port and are in folding state.
That's
switch 1.
false.
False. Okay. Switch 1 is selected as a root bridge by comparing the bridge ID. Correct. Okay. Some question about the H port. Which of the following statement is true about the H port in RSTP? Select 1. H ports participate in RSTP calculation. False. Interconnected. Okay. Oh, Dr. Bala,
D is correct. D is true.
Okay, D is true. The H port can directly transition from disabled state to folding state. Yes, this is the true statement. Okay, next one. Which of the following port states are included in Rapid Spanning Tree Protocol, RSTP? Select 1 or more. Discarding.
Learning.
You say learning.
Forwarding.
Forwarding.
Discarding, is it?
Discarding.
Yeah.
Okay, only 3. Yeah? Which of the following ports rows are added to RSTP compared to STP?
Backup port, alternate port.
Backup port, alternate port. You're right.
Yeah.
in which of the following states does an SDP-enabled port participate in the port row election? Select one. So which port state is the election run?
Which of the following states does?
Is where the port row election is ongoing.
Listening.
Listening, correct.
Yeah.
Yes, correct. Which of the following is not the reason why RSTP can increase the conversion speed? Select one. The forward delay timer is cancelled.
PA? What's the PA?
PA mechanism, proposal and agreement mechanism. This is the core of the RSTP. So it's true, this one. This is the reason. Quick transition between root port states.
H port, I think.
H port, is it H port the reason? Yes, H port is the reason because the end devices does not need to wait the ports to go to listening port, learning port, learning state, listening state, learning state, and then forwarding state. No need to wait. It's also part of the converge, just not part of the election. Okay, converge. Okay, so first one is not the reason because the forward delay timer it still exists. It's still there. It's not cancelled.
Yeah.
So that's some question about the forward delay timer. In which of the following scenario does the forward delay timer exist? Select one or more. Which one?
Forward delay.
Transition from forwarding to disable, learning to forwarding. Yes.
Forwarding to disabled.
No.
You sure?
Sure.
How many seconds is between the learning? And, is it 15 seconds, right?
Forward delay is 15 seconds.
Right. Okay. Okay.
Listening to learning.
Listening.
Yes. Listening to learning 15 seconds. Learning to forwarding 15 seconds.
Okay, that's 30.
Okay, yeah? That's all. Okay, so okay, you already 7:15. I think other question we can try maybe in other days we can try this. So let's continue to the topics.
I think I'll have to leave now because I have a class myself.
Okay. Sure.
So I'll see you tomorrow.
Okay, see you tomorrow.
Okay, bye.
Okay, so some question here. So well, how about we take a 10 minutes break? We're done the question for 1 hour. It's okay. So take a 10 minutes break. Just 10 minutes.
12 minutes.
10 minutes. Okay, continue at 12:25. Now it's already PM.
Oh boy, might get on. Sure.
Who is that? Huh? Hello, what happened? The question has been uploaded now. I can't quiet. Who is that? That's what I'm saying. I've started it now. The who is doing? So if there's any student that calls you, let them know. Some have.
Okay. So now we are going to the new module, which is the routing. Okay, we talk about routing. We are talking about, now we are going from layer 2, go to layer 3. This layer 3 technologies, because we are going from one network to another network. This time we need routings. Okay, so we start with this, the basic knowledge of IP routing. Okay, okay, some forward. The forwarding of frames and switching has introduced the data link layer operations. This is what we have learned. Then, with the introduction of routing, the physics that define upper layer protocols and inter-network communication are established. Okay, and an enterprise network domains generally consists of multiple networks for which routing decisions are needed to ensure optimal routes are used in order to forward IP packets to intended network destination. This section introduces the foundations on which such IP routing is based. So in this section, I will explain the principles that governs the IP routing decision, means how the router make decisions on how to forward a packet. And I'll explain the basic requirements for packet forwarding. Okay. So autonomous system is an IP network or networks controlled by one or more operators with a clear policy that governs how routing decisions are made. So, an autonomous system is a very big networks. It's a very big one. Inside the autonomous system, there are many networks. You can see here, example here is have 5 broadcast domains, 5 networks. This is just 6 routers. Actually, an example of an autonomous system is ISP, such as the carrier, your telecommunication provider, like the MTN and the GLO, like AT&T or Vodafone. All these ISP are autonomous system because their network is very big. So all the subscribers like us, we subscribe to the package, subscribe to the phone package. We connect to the internet. Actually, we are connecting to the ISP. So we are part of the ISP autonomous system because we are under we are connected to their networks. So ISP can route our packets to all around the world, to the other country, to maybe other servers at other country, at other data centers around the world actually. So under this autonomous system have many routers. So the ISP, the engineers, administrator in the ISPs have using a clear policy, have implement a clear policy, means a clear routing protocol, routing policy, so that control that manage how the routing decision of all these routers, so many routers, how they do it. Okay, this is what we learn in this topic. So local area network and broadcast domain is mean the same thing. One local area network means one broadcast domains. So again, routers separate the broadcast domain. Okay, cool. Okay, so router, so there's a 1 LAN, 2 and 3. 3 LAN, 3 broadcast domain. Okay, next one. So routing decision. Routers are responsible for the decision-making process that determines the path via which packets are forwarded. Okay, so if you stand on this router, this is your destinations. So how routers can make decision. Should I forward to this router or should I forward to this router? Because both path is valid, is possible. Which one is better? Which one is the best path, most optimal path? How the router make the decisions. Okay. How router make the decision is based on the routing table. A routing table is just like a guides, a map. Tell the router, okay, if you want to go to this destination, go to this router, next hop. Okay. So in the routing table, all the routers, even the switch, layer 3 switch, and our PC, all the device have routing table. So this is the example of the routing table of the router. So here we have destination, where you want to go, your destination, your protocol. Okay. This route means this destination, how you learn this destination. Maybe from the direct connected network, maybe static, maybe OSPF, maybe it's RIP, or maybe it's other routing protocols like ISIS is possible. So, and for each of this protocol, they have their own preference value. Okay, preference. And then also have the cost. So these are the 4 criteria that been used to make the decision. You compare these 4 criteria. And then after you decide which one, and for each of the routes, which of the destination have their own next hop. You should pass to which router or which IP address. And then you should go out for which interface, output interface. Okay, means in this example, for this router, this is the destination network. This or this is the next hop.
Sorry, Mr. Mike. Sorry, Mr. Mike.
Okay. Okay. Yes.
Please, can you go back to the routing table there?
Yes.
Yeah. What's the PRE for?
PRE, preference value.
Okay.
Okay.
Thank you.
Okay, again, so this is the destination, this is the next hop, this is the next hop, and this is the output interface. Which interface is going out to your next hop, to that destination. Okay. So the IP routing table lists the networks that are reachable via the router. Packets that have no routes are subsequently discarded. Means that when the router receives a packet, the router reads the destination IP address. Then the router looks at the routing table. I don't recognize any, I don't know how to go to this IP address, so I discard. If I discard, I will send a ICMP message back to the source IP address, telling him maybe network unreachable. Mostly it's like this, network unreachable. And then how the router doing the decisions. The first one is compare the destination network. So destination, if you have only one route to go to that destination, then it's easy. Just select that routes, that next hop, next hop. But if you have some similar, almost similar destination, let's say this is router A routing table. Now the destination is going to 10.1.1.1. Okay, going to router C. So going to router C, inside the IP, the routing table, we have 2 static. Okay, we have 2 static routes. Static route is manually configured by administrator. And then you can see the destinations 10.1.1.0, 10.1.1.0. What the difference is the subnet /24/30. Okay, now the destination address now going to is 10.1.1.1. to router C. So which one is the longest match? 10.1.1.1. Match which destination the most? Okay, let's see. 10.1.1.1 is our destination IP address. So in our routes, we have 10.1.1.0/24, 10.1.1.0/30. Okay, you must be aware that this one, the routes here is the network address. It's always the network address, not the IP address of a device. It's a network address. Means that you are telling the router, if you want to go to this network, well, who is your next hop? Which network, not which device or which IP, is which network. Okay. Okay, so how to differentiate? So 10.1.1.1/24 means the first 24 bit is the network bits. For this /30 means the first 30 bits is the network bits. So yeah, 30 bits are network bits. So for this IP address, we check is 10.1.1.000000001. Okay, so how many bits I match? So for this is my network bits until here. So for this is my network bits. So if you compare this and this, you only match 24 bits for 10.1, 10.1. You compare with this, I can match until 30, bit 30. Yes, until the bit 30, I also match everything. Okay, match everything here. So this will be the longest match. So this will be the best route. Okay. Next, if both destination network is the same, 10.1.1.0/30. 10.1.0/30, 10.1.1.0/30, and then both the router A learn this network, okay, using OSPF and RIP, because this router use RIP to tell this router use RIP to tell this router about this network. This router also can use another routing protocol, OSPF, to tell this router. This router also use OSPF to tell this router. This router also use OSPF to tell this router about this network. So this router learn this network through OSPF and RIP. Okay, so means that there will be another one, 10.1.1.0, 10.1.1.0/30, and then the protocol will be RIP. Okay, now then the preference is for RIP is 100. You see, OSPF 10, RIP 100. So if we just comparing the destination and mask, 10.1.1.0/30. This also 10.1.1.0/30. Which one is the longest match? Cannot decide because both are the same. So you cannot decide. Then only we move to next one, protocol. Okay, OSPF and RIP. So what are the preference for these two protocol? Preference, OSPF is 10, RIP is 100. And okay, how do we decide? Okay, listen. The lowest preference value is the best. Okay, the protocol with the lowest preference value. preference number, I mean the preference number, the value is the best, is better, is the best. Huh? Okay, means that OSPF is 10, RIP is 100, means OSPF, the preference is lower than RIP. So OSPF is the best path, is a better path, better routes.
Hello,
Okay.
Mr. Bear.
Yes.
No, please, the calculation again, please.
Okay, so how to compare the preference value? So the lower the preference value, the better the path. Okay, the lower the preference value, the better the path. Okay, so for router A, you will choose this router as a next hop for this destination network, and this is the output interface. Go out from this interface, this is the next hop. Means that this one, how about this route? This will become a backup. If this link is down, maybe this will become a active. Okay. So direct route is 0, it's always 0. So the direct route means all the network that directly connected to the router, direct connected. So 0, always the best. Preference 0, the lowest 0, the best. OSPF is 10, static is 60, RP is 100. Okay, and all this can be changed. Okay, can be changed, except the direct routes. Okay, so this is by default, 10, 60, 100. And then if both with the router, okay, the router learn the destination network or using same protocol, or both are OSPF. Okay, what happened? Same network, same protocol, same preference. Okay, then we have to compare the cost. Okay. So for the path above, on the top, the cost of the metric is 100. On the bottom, the cost is 50. So the lower the cost, the better the path. So this router will choose this router as the next hop. This is the output interface. This is a network. So we have three things: destination, next hop, and interface. Okay. All the between here, the preference, the cost, just to make the routing decisions. After the decision is done, so the most important is you must know where are you going. Okay, where are you going to, and who are you going first? Okay, what is your destination? So which one is your next hop, and go out from where? Okay. Okay, next. So to establish a routing table, okay, you can see this is the source. This is the protocol. So you can see the Chinese word here is because the training material some defects on they miss out to translate this. So this means protocol. This means destination network. This means output interface. What do you mean? Okay, direct. How the router A learn all this. Okay, I'll explain one by one. So the router learn network 10.1.1.0 from direct routes, direct connectors. So if I want to go, if router 1 want to go to network 10.1.1.0, this is the output interface, G1. So how the router learn network 192.168.1.0. configured by administrator. Output interface based on the actually it's based on the where is your network, and then who is your next hop. Here never mention who is next hop, but we know that the next hop is the output interface is G0, means that this is G0, so only have two paths. So router A have to send to this next hop, or send out from this interface. Send out from this interface. Also can. So what do you mean is the router, this router doesn't care at all. Do not care. The packets will pass through this router, this router, this router, this router, then only reach the destination. The router doesn't care about that. You just know that, okay, following this destination, I forward the packet out from this G0, forward out, then my job is done. Okay, the packet, the next router will handle the packet. So the next router will have its own routing table. This router also have its own routing table. This router also have its own routing table. This also has its own routing table. So forward, then this router have to make a decision. Then forwards, make decision again, forward, then make decision again, then forward, make decision, forward. Okay, and then OSPF. The router also learned about this network. 192.168.2.0 is this one. Truth OSPF, and the output interface is G0. Also the same path. Send out, send out. Okay, next one. So a routing table forwarding requirements. The forwarding of paper packets require that the destination be known, as well as the forwarding interface and next hop. So if you want to go to a destination, you must recognize the destination first. You must have this destination in the routing table. And then the destination need to have the output interface and the next hop IP, means your neighbor, okay, to be valid. Then this is a valid routes can be used. Okay, these three things. Okay, so you also see under the routing table, you also can see this. D. Okay, what do you mean by D? Download to FIB. FIB means forwarding information base. Okay, forwarding information base. So from here, please follow me. Take out around. You can save the topology and then you open a new topo. Okay, in your ENSP, please. And then you take out the two routers. One router, two router. Router, the name of router is the generic router. R1, R2. And then you start both router. Okay, and then you can connect G0 to Z0. Yeah, connect. And also you connect G1 to G1. Okay, don't get it wrong. G0 to G0, G1 to G1. So I advise you always turn on your interface, show all interface, turn on. So So I would like you to create some loopback, and later we'll configure some IP address. Loopback 0 on R2. You create a loopback 0 with IP address 2.2.2.2/32. So for network above between R1, R2 and G0, you put the 1, 2, address 12.1.0.0 space 24. This is subnet mask. Bottom is 12.2.0.0. So it's 24. Make it better. Just put it .1. This is .0. Okay. Okay. So what I want you to do here is G0 means it's better for us to reference. 1, 2 means between router 1 and router 2. .0 means G0. Okay, then .0.0/24 is a subnet mask. So for R1 is .1, for R2 is .2 for the last number. So the bottom here is also 1, 2 between R1 and R2. 1, 2.1 because it's G1. And then .0. R1 is .1, R2 is .2. So /24. So we'll configure this. Okay. Okay. So what is the order in which routing decisions are made? How the router make the routing decisions?
Okay.
It's the order. What is the order?
Did you say we should design that topology?
Yes, or it's okay, or I just drop into the
Yeah.
It's faster.
Okay.
So IP routing. Okay, please get the topology from the WhatsApp group, and then extract. Remember to extract. Right click to extract. Okay, so we continue a bit with the slides. Last quiz, some summary. So the router made the routing decision based on the first one, longest match, and then only preference, and then only cost, or we call the metric. Okay, if the cost also the same, right, then we have an equal cost multi-path. Also, we say equal cost path, and then this is the router will do load balance. So the traffic will separate to two paths, or separately half 50-50. Okay, so there should be less congestion. So both the path can be utilized. So what does the preference represent? Preference represent the preference of the routes, how the router learn the routes, and use the routing decisions to help the router to do the routing decisions. So the lower the preference value, the better the route. Okay.
Yep.
Okay. So for IP routing, let's see. Oops, what happened?
No, Mr. Ben, can you hear me?
Yes.
Are we starting the devices?
Yes, please start all these are two routers, so yeah, please start the router. Okay, for IP routing. Okay, for IP routing, we have three types of routes, as you have seen. Okay, first one we have direct routes, and then later we learn is static route, this manual configure, and then we dynamic routes. So dynamic routes, under dynamic route we have IGP and EGP. So IGP is we call interior gateway protocol. So this is what the ISP use inside the AS, the autonomous system. So inside AS, we have two types of dynamic routing protocol, two categories. One is distant vector, one is link state. Distant vector is based on the concept of next hop, by hop count, doing hop count. We have RIP, RIPv2, RIPNG, and EIGRP. For link state, we have OSPF and ISIS. This is used inside the AS, inside one ISP network. So, but if the ISP want to route your packet data over to other country, to other ISP in other country, they need to use EGP, exterior gateway protocol. So this is to route the traffic between AS. So under this, we have a BGP, border gateway protocol.
What was the AS again?
Autonomous system.
Okay.
Okay. So this is EGP, is a category, and then the name of the protocol. Border gateway protocol is used by ISP to send the data to route your packet to another ISP. Okay. So in this IARES, we only learn static and OSPF. Okay, only these two we learn for routing. Direct, no need to learn that because this is direct connector.
No BGP?
No, BGP is in professional level.
Oh,
because BGP is allowed to talk. Not enough time.
Okay.
Because for professional level, the full track is 15 days. But normally we just run 10 days. Okay. Fast track is 10 days. Okay, so it's allowed to talk in professional level. Okay.
Would it be possible to join the BGP training, or would you have it?
Or do you mean just a training just for BGP?
Yes.
That need to be. This is a custom. This is a customized training, or you can just apply, register to join the HCIP, the professional level training also can. So we not in that level. We not only teach a BGP, we also teach MPLS, IS also have. We also teach VPN and many more technologies. Okay.
Okay. Thank you.
Okay. So I close this. So now we are learning static routes. Okay, IP static routes. The implementation of routes within the IP routing table of a router can be defined manually using static routes or through the use of dynamic routing protocols. The manual configuration of routes enable direct control over the routing table. However, may result in route failure should a router's next hop fail. The configuration of static routes, however, is often used to complement dynamic routing protocol to provide alternative route in the event dynamically discovered route fail to provide a valid next hop. So knowledge of various applications of static route and configuration is necessary for effective network administration. Okay. So at here, what you need to know is the static route is manually configured. So what happened is if the static route, what happened to the static route is it will fail if the next hop, because you configure the static route, you have to mention what is the network, the subnet mask, and the next hop IP address. So if the next hop, the router next hop is failed, so means your static route is not valid anymore. But because it is static, this manual configure, the router doesn't know how to adapt, automatically change, intervene the routes based on the topology, the network changes. Cannot, because it is static. That's why we have the dynamic routing protocol, because by using dynamic routing protocols, the routers can negotiate, they tell each other, okay, what happened, topology change, network down, anything, they tell each other. Then your routing table will keep on updating to valid routes to get the best route and the most optimal path. Okay, but here also static route also can be alternative routes in the event the dynamic protocol is failed. Okay, so you have pros and cons between static route and dynamic routes. So I will explain how can you use the static routes in different scenarios, different applications. Then we will configure the static route in the ENSP. So where normally you use you can see the static route is your gateway. Okay, normally we see this at home. Okay, static routes define the means of path selection to other routes. Okay, what do you mean? Mostly we do static route is we point to one directions. We do the default routes. But this is all the private networks. Private network, we have VLANs. We have the layer 3 switch to control the traffic. But when you go out, for all the traffics, for all the destination network that the switch doesn't know, means it's going to the internet. So for all the routes, the switch will forward to the router. The router is the device that can connect everyone to the internet, connect to the WAN, wide area network. So the router will forward everything. Okay, what the router doesn't know how to go, forward everything to your ISP. ISP will send the routes to other routes to other ISP also can maybe. So this is static, how we use static, because we know where we want to go, and we doesn't need the dynamic routing because dynamic routes, because they need to do calculations. Routers need to send protocol packets to each other. This also consume bandwidth. They will negotiate, advertise the routes. So this will consume CPU resources to do the calculations. So the more the routes, the bigger networks, the more the workload on the router. So if for small enterprise or home network, we doesn't need usually we cannot afford a high-end router, a good amount. So use a low-end router, or you can just use a home router. Okay, so home router don't need to do can just set the static route and ask the router forward everything. You don't need to do no need to do any calculations. Just set the default routes. Send everything to the internet, send to the ISP, then done. So no need to do any calculations. Okay, so static route behavior. The forwarding of packets based on serial interface require that the outbound interface to be defined. So it depends on which type of cable you're using or interface. If you are using serial interface, which is a legacy interface, so you have to define the outbound interface. So means that you just have to define your destination network and the outbound interface. You doesn't need to define who is your next hop because this is one-to-one. This is serial. If you are using broadcast network, means you are using UTP, you are using fiber, all this Ethernet network, IP networks. Okay, Ethernet network. Why we have Ethernet? Because only Ethernet have broadcast domain, broadcast frame. Serial, no broadcast. Serial also don't recognize MAC address. So only Ethernet technology recognize MAC addresses, and then you may have unicast, multicast, and broadcast. Okay. So this is why do we need to care? In this example, this is also a broadcast. Even though you see one router, one-to-one, one router, one-to-one. Okay, this is because this is using the Ethernet cable, the UTP or the fiber. And then in the broadcast, what we learned until now, everything is Ethernet network, IP network, or you need to use it's all a broadcast network. So forwarding packets over broadcast network such as Ethernet require that the next hop be defined. This is because serial is always only one-to-one. Okay, but for broadcast, if this is the coaxial, because inside one network, you may have 1, 2, 3. Okay, you may have three hosts, 3 ports, 3 hosts in the same network. So you must define who is your next hop, so that the packet can be forwarded to the correct destinations. So let's say for router B, router B want to go to send data to this network 192.168.3.0. So what you need to do is, in the destination, what is the destination network? The destination IP address is 192.168.3, maybe .3.1. Okay. Then this is the packet. The destination IP packet, the destination IP address in the packet will be 192.168.3.1. And what is the destination MAC address in the Ethernet header? It will be the MAC address of router C at this interface. Okay, so how the router can know which MAC address put on the Ethernet header destination MAC address? That's when you define the next hop. Okay, next hop. You will define this is my network. This is my next hop. This is my output interface. So the router can encapsulate the router C MAC address as the destination MAC address. Then the packet can be forwarded to router C. Router C can forward the packet to the destination. Okay, so this is a command, configuring a static routes. The command is IP route static. Okay, this is standard command, IP route static. And then behind is the destination network, the network address. And then behind is the subnet mask. Okay, subnet mask, and then is your next hop. Next hop. Yes.
Sorry, I have a quick question. Can you go back again to the diagram on the next hop? Yeah.
This one? Yes.
Yeah, I see in between router B and router C, the next hop is the next hop not 10.0.123.0?
This is the network address. This is the network address.
Yeah. So the next hop to add router B and C, I'm trying to understand.
Oh, I see. Okay, when you define, you put the next hop, which is the IP address of router C, 10.0.123.3 for this destination.
123.3, yes, ahead, okay.
Yes.
Yeah, okay, that's right.
Because it's same network, right? 123.2, 123.3, same network. So router B will send a ARP request.
Yeah.
Look for the MAC address of
that's okay. That's
C.
okay. That's fine.
Okay. Yeah. Next. Okay. So here, this is the next hop. Which this is router B. Router B. So on router B, I configure IP route static. This is my destination network address. This is my subnet mask 24 or equal to 255.255.255.0. Or you can just put 24 also can. And then who is your next? My next hop is this 10.0.12.1. And because this is serial, you also can just define the output interface S1000. Okay. So about the subnet mask, you can either put the full subnet mask or just put the prefix. Okay, the prefix is better, right? Because that's 2 numbers. Huawei can do this, but Cisco cannot do this. Cisco must define the full subnet mask. Okay, now how about we start to configure? Okay, so I believe you have started your device. So I open all CLI, keep all CLI. So you adjust your tab. R1, put at the first one, then R2. So we configure the R1, SY, system view, SY space R1 for sysname. If something pop up when you type in your command, press tab. Press tab. Okay. System view, go to system view and then configure the host name of the router, sysname. Okay, sysname space R2 or just put the shortcut SY. Okay, then we configure a IP for interface. Let's say G0. Okay, GE000. I just call it Z0. The bottom one we call it G1. So interface, the full one is interface, or you just put INT also can. Space G0/0/0 for G0. Configure the IP address. Let's put IP space ADD RESS. IP address space 12.0.0.1 space subnet mask 24. Enter.
Are we configuring R1, sorry?
Yes, we are configuring R1. Sorry, I put wrong. The system is wrong. SY R1. Should be like this. Then I made it. I create again. So what you should do is SY system view and then sysname R1 and then interface G000, then IP space address 12.0.0.1 space 24, then enter. Enter.
Okay.
Okay, so we have another interface also we configure at the same time. G1. So on G0 under here, you also can just straight type int space G0/0/1. Enter. And then IP address space 12.1.0.1 space 24. Enter. Okay, then you check display space IP space int interface space BR for brief. Enter. You got it right. Now you check. G0 is 12.0.0.1/24, correct? G1 is 12.1.0.1/24, correct?
You're running a display int.
Yes, Bala? Yeah.
Display IP int.
Okay, again, this one. The full command is display IP space interface brief. Copy down this command.
Yeah, the two are up.
Yes, same. The IP address is correct. Okay, then go to R2.
R2.
Okay, system view. Or just SY also. Okay, then sysname R2. Okay, R2. And then interface G000, IP address 12.0.0.2 space 24 and then interface G001, IP address 12.1.0.2 space 24 and okay, and then I want you to configure a look back as I put a label on the topology. So interface space LOOPDAC, look back 0, enter, and the IP address is 2.2.2.2 space 32. You see the subnet mask is 32. Well, this is a logical interface. Enter. Okay.
Ajar. Gaskiya muna abu. Me ba ne?
So display IP interface brief. Enter. Check. G0 12002/24. G1 12.1.0.2/24. And then the loopback. The loopback is 2.2.2.2/32. Okay. Okay, so we have finished configure all the IP address. Okay, on the interface. Now we go back to R1. Then quit. So display IP routing table. Okay. I'll check the routing table of R1. Display or just this DIS space IP space routing dash table. Enter. This is the routing table of R1. You can see there's the destination, protocol preference, cost, and the next hop, and the output interface. So it's whole line at here, and then because it's it's too long, this is the next line here. Okay, interface is G000. But this is all direct routes because these are the network direct connected to the router 1. Okay, so you notice this one, flag D, download to FIB or download to FIB. FIB is the forwarding information base. So the IP routing table actually it will store all the valid routes. Either is the valid routes, it may be not the best, it will store everything here. Okay, but it will only show the best for you. A routing table at here, just put the display IP routing table, you only see the best route and their protocol preference and cost. Okay, but after what happened is after the routing table decide, okay, I have this is my best route, and then I will download to FIB. So display FIB. DIS space FIB. Display FIB. Enter. Then you will see all these routes are downloaded from the routing table to FIB. You can see at here because the routing table already do the, or you can call the routing table is in the control plane, okay, management plane. The control plane have to decide the best route, do all the decision based on the destination mask, longest match, the protocol, the preference and the cost. Routing table done all the decisions and pass download to FIB. So that's why in FIB, all is best route. You only see the destination, the next hop, and the output interface. Only these three. 1, 2, 3. In the FIB. So all the packets that being forwarded to router 1 router 1 will send to, will decide, actually router 1 will, because router 1 already, the routing table already set. So everything will be sent to the forwarding plane. Forwarding plane, the packet will be sent to forwarding plane. Then based on the destination IP address, then it will be sent to the next hop and then send out from that interface of this. So here, all is the best. No need to compare anything anymore. In FIB. Okay. So now I want to ping R1 ping 1.1.1.1. Is it possible? Cannot. Request time out.
There's no loopback 1.1.
There is no destination network 1.1.1.1. So we can use static route. IP space route dash static. IP space route dash static space destination, the network address 1.1.1.1, subnet mask 32 space next hop 12.0.0.2. That's all. Enter. Okay, now you ping again. Ping space 1.1.1.1. Enter.
I think the loopback is the 2.2.2.
The 2.2.2.2.
Oh, sorry, yeah. Ping 2.2.2.2. But you also
have to
failed.
reconfigure the static route.
You are correct. So how to do it? Display this. You have the static route here. Okay, you can just undo space IP route dash static. So whatever command you done is wrong, you can use undo. And you just configure, type the same command. 1 space 24 space 12.0.0.2. Enter. Undo.
Yeah, 2.2.2 is live.
Oh, I should put 32. Okay, yes, also okay. Display this. Oh, no. Maybe I just copy everything. I like copy, undo.
Undo is wrong. The spelling.
Wireless class.
Yeah.
Wireless class.
Okay, display this is gone. So again, IP route static 2.2.2.2 space 32 space 12.0.0.2. Enter. And then ping space 2.2.2.2. Yes, success. So display IP routing table. What you have? 2.2.2.2/32 static. Learn from static because configured by static. Then preference by default static route is preference 60. And then next hop 12.0.0.2. Output interface is 0, G0. Display FIB because you see download here 2.2.2.2/32. Next hop and the output interface. Okay. How about I have another path? I have two next hop. How about I configure the another one also? IP route static 2.2.2.2 space 32 space 12.1.0.2. Enter. Okay. Then display IP routing table. Enter. You will see one destination, you get two next hop. Because this is equal cost multi-path, same protocol, same preference, same cost, 0, 0. So this load balance means one down, I have another one is running, is up. Okay. So this is what we call static route load balancing. Okay. Static routes support load balancing to the same destination where the cost of routes are equal. Okay, you get it? The configurations. Everyone can follow. You can. Let's continue to the next one. Okay,
sorry,
verify
guys, I have
this.
to run now. I'll be back later.
Sorry, Mr. Bay, go back a bit.
Mean this one, or the topology. This one.
Okay, so we're configuring the IP route static command on the route and not on the loopback, right?
On the R1, same.
Yeah, on the R1 interface, not on the loopback interface, right?
Yeah. My destination still the 2.2.2.2.
Okay, it's okay.
And I use my another next hop. Yeah.
Okay.
This is my destination. This I have two next hop. Okay. So this route balancing, so floating static routes is where floating static routes provide an alternative route in the event that the primary static routes fails. So we can configure one active, one backup. Means only one is up, another one is not using it. It's up, but it's not using. Okay, all the traffic will go to the primary. When the primary is down, then only the backup. Means the floating will float to the surface. Float, it will be seen, then can be used the route. So how to do it is by changing the preference value. This is how you change the preference value of a static route in the command. You add on the command. So here, you go back to the same. We configure one of the static route to become the floating. So IP route static 2.2.2.2 space 32 space 12.1.0.2. Okay. Space preference space question mark. So you can put the preference 1 until 255. By default, is 60. So mean your next hop to the route which the next hop which is 12.0.0.2 is 60. Now I want to change this route, this 12.1.0.2 to a backup route. So I must put the preference value greater than 60, at least 61, 62, or 100, or 255 also can. And if I change this, put the preference to 59 or less than the 60, means that this route will become the active. The route, the next route 12.0.0.2 will become the backup. Now I want this to become the backup. So I may put 99. Succeed. So display IP routing table. Now you no more seeing the next hop to 12.1. Only one route. Okay, but I got another command for you. Display IP routing table. Same. Display IP routing table. Not this, not this. IP display IP routing table protocol space static. Only show the static route in the routing table. So you will see this active static 12.0.0.2. Inactive means the backup. Also the same 12, but the next one is 12.1.0.2. Preference 99. Preference 60. Okay, IP, and again, display IP routing table. You only see the 60. And then display FID. You also only see the this one 12.0.0.2, only one. Okay, so about I go into interface G000, and then you shut down the ports, means shut down the link, shut down the ports. So now G0 is down, means the link 12.0 is down, means 12.1 should be up, should be kind of active. So now I display IP routing table. Display IP routing table. Enter. You can see still 2.2.2, but now is the preference 99. Next hop 12.1.0.2. Okay. And then this quick display IP routing table, protocol static. Enter. You can see now the active is the preference 99. The inactive is the preference 60. Then you still can ping 2.2.2.2. Okay. So this is floating static routes. Okay, everyone. Okay. Managed to follow.
I'm struggling on the Zoom now.
Okay, so you go to the last one. It's the default static routes. Last one already, huh? So this is how you configure default static route. How? Okay, example here is router A.
Okay. Still like 1 hour.
Okay. So example here is router A. On router A, router A want to go to this tree network. So according to the command we learned before, if I want to go to this network, I should configure IP static route, this network, and then this next hop, this network, this next hop, this network, this next hop. And you configure 3 routes, 3 static routes to go to these 3 networks. So instead of that, I can just configure a default routes. Default routes. This is the network address. This is a subnet mask. Either .0, it can be .0.0.0.0 or just a 0. And then my next hop is router B. Means that this route is the last resort route in the event that no other longest match is found within the table. because this route can match any network. Mostly for your PC, this is your gateway. The next hop for your default route is your gateway. You can check. Open a command prompt, route pre -4. Then this is the routing table of my PC. So I can see destination 0, mask 0, gateway 10.11.250. This is my gateway. Means that I have this. Then only I can go to internet. Means I want to send everything. I want to go internet. I go to my gateway. Then my gateway will route my data, my packets. Go to the internet. So longest match. So longest match also appear in the IP routing table. So what I want to do is go back to R1. Okay. And go to R2. I want you to go to R2. R2, system view. I want to configure another loopback interface. Loopback 1. IP address 22.22.22.22 space 32. Okay. So that I will go back to R1. Configure this first. R2 interface loopback 1 IP address 22.22.22.22 space 32. Okay, then go back to R1, display this. I want you to remove these two routes. So I copy this, copy, undo, space, paste, copy, undo, space, paste, display this. Okay, it's gone. So I want to configure default route, default IP route static 0.0.0.0 space 0. Then, because I already shut down the port, never mind, just configure to 12.0.0.2. Another one, IP route static. So 12.1.0.2. I have two static routes. Two default static routes. Now I want you to go into G000 to undo shutdown. Undo shutdown. Okay. Then to turn on the port G0. After that, display IP routing table. I should go to here, display IP routing table. Okay, space protocol static. Let's see what I have. Okay. Active, you have two routes. Okay, two routes. This is the destination. Static, one hop. This is another next hop. Okay. So display IP routing table. You also can see the same thing. And then display FIB. Also, you have 2 routes. Of course, you can try to ping 2.2.2.2, enter, success. Ping 22.22.22.22, success. Okay, another one. I want you to try to ping one more.
Hello, Mr. Bay.
Yes.
Sorry, I don't know.
Yes.
I was just following up on the exercise. I can see my interface showing the 2 interfaces for G0 and G1 having 12.0.0.2 and 12.1.0.2 on R2. I also have the loopback interface 2.2.2/32. This seems they're all up, but to my surprise, if I run the IP route static 2.2.2.2 space 32 space 12.0.0.2, it gives me the next hop address is invalid.
Where you configure the IP static route? I configure R1.
No, I configured R2. And
where you configure the static route at R2?
Yeah. So
that is wrong. That is wrong.
Pardon?
You should I configure the static route at R1.
Okay.
Because this is for R1 to go to a network directly connected to R2. So R2, for R2 have the network already, you see in R2, you display IP routing table. There's already 2222 and this one already direct connected. You don't need to configure any direct static route to go to this. No.
Okay.
So that's why it's wrong.
So it should have been on R1. Okay, that explains.
Yes. R1. Okay. I want to tell R1 how to go to R1, how to go to network 2222.
Okay, sorry. It's okay.
Okay. Okay, in R1, I also can try to ping someone. 1.1.1. I know that this will be request timeout as expected. Request timeout. So those can follow. Please go to R2, configure static route IP route static default route 0.0.0.0 space 12.0.0.1, which is router 1. Enter. Okay. Means that now I have a static route for R1. Next hop is R2. For R2, next hop is go to R1. What you can see? Can you see a loop? Can you see a loop here? Okay, you will see what the effect. R1. Now R1, I ping 1111. I get request timeout. I ping again 1111. I think do I get the same thing? No, I didn't get it. Also request timeout. Request timeouts. Well, it's not. Let's see. Capture data. G0. Okay, we already see this. Huh? I capture again. I already saw what I want. Okay, R1, I try to shut down my G1. The phase G1 shut down. Okay, again. Data capture G0. Okay. Pin question mark. I just want in C. Okay, it's C minus C1. I just want to send one ping packet to 1.1.1.1. So what I get? See my Wireshark capture. Right? Okay. 256. What is this? Why? See? What happened?
Do we actually have 111 as part of the network?
No,
IP?
we don't have.
So who have any response?
So what the default routes? I configure default. Do you at R2 do you configure default routes? This one?
That's a good to of.
Yes. So now what I have is R1 have a default route pointing to R2. R2 also have a default route pointing to R1. What happened here? Can you see something? Whatever R1 doesn't know, that means that I ping 111 destination 111. Router 1 doesn't know is it. Forward to R2. Router 2 check destination 111. I don't know. I follow my default route forward to R1. R1 check destination 111 forward.
Yes.
Keep on forward.
Okay.
Keep on repeating until the it's dropped. Why? Because the TTL reached 0. That's why you can see this first one sent out by R1. Then you see that's the MAC address A2 B4. Next one B4 A2. Next one A2 B4. Repeat. They send back through and fro until the time to leave 1. Last one. Time to leave 2, 5, 5. This is time to exceed. Okay. Time to leave 1. Then gone. Time to exceed. Sent by R2 to tell R1. TTL exceeded. So this is a routing loops, but it can be stopped. It can be stopped by the TTL. Okay. But what happened is your packets will never go out. So will never go to the correct, able to go out to the internet if something happened by this, it happened in your network. So the best practice when we configure the default routes, we also always make sure you're only pointing to one direction. This, if your router one pointing to router 2, your router 2 should pointing to another device, another router. Okay, you should never point it back. No, make sure your default route is face to one direction only. Okay, maybe this is the internet or another router. Okay, so this router might be also pointing to the same direction. Another one, don't point back.
Hello, Mr. Ben.
Yes.
Internet like ISP.
Yes. Your signal is not good. I can't hear you.
Okay. The arrow should point to an internet, meaning an ISP.
Sorry, Lucky, I can't hear you because your signal is not good. I cannot hear what you are saying. Okay, or maybe you can try to type into the WhatsApp group. Okay, let me see. Okay, so that's all for the static routes. So what should be altered to enable the static route to become a floating static route? The preference. Okay, and which network address should be defined to allow a default static route to be implemented in the routing table? The network address is 0.0.0.0. So what I can say is all your network devices in your private network, maybe in your home or either in your enterprise, if you have like your universities. So if you have a very big network, you have many network devices. All your network devices should have a default route point to the gateway. Okay, because by default, switch and router do not have default routes. You have to manually configure. But for your end device, they have default route because you configure the gateway. So a default route is just like a gateway for your switch and for your routers. So it's very recommended you configure default route as a gateway for your router and switch. Okay, thank you for this topic. Okay. So it's almost 9. Let me see what we still have. Okay, today we are going through the spanning tree, RSVP, and this IP routing basic and the static routes. Tomorrow we will go into the OSPF. OSPF, short link is a link state routing protocol. Link states. So it will tell what is the state of the link. State of the link can be like the link is a port. What is the speed of the link or speed of the port? So this is how the OSPF will consider. Later we'll check. You see, so OSPF is an integral gateway protocol, as I already explained, mentioned to you. IGP. OSPF is used in intra as mean inside the AS. It can be used inside the AS, or it also can be used inside a SMB. It's a small network, private network. Maybe you have 2 routers. You can do OSPF. Also can. That is found on the principle of link state routing. The link state behavior provides many alternative advantages for medium and even large enterprise networks, just like ISP. Okay. Its application as an IGP is introduced along with information relevant to the understanding of OSPF convergence and implementations for supporting OSPF in networks. So in this section, I will explain the OSPF conversion process and describe the different network types supported by OSPF, and we will configure a single area OSPF. So this OSPF, let me go through with some of the characteristics, then we'll stop. So before we go into this, okay, let me explain. Let's say I have many routers. Okay, let me just take an example only to tell you a route. Okay, just connect. I just want to do an example. Let's say maybe I have here, I have another network. Look back. 3.3.3.3. 4.4.4.4. Okay, so if I'm using what? If I'm using static routes, what should I do? If I want to go to 3.3.3.3, I should configure a static route. This is a next extension network. This is my next hop. If I want to go to 4.4.4.4, in terms of for R1, actually for R1, my next hop is R2. So you have to configure all this. If there's another network, somewhere here, another network, so you have to configure again. Next hop, this one. So if there's more network, this network maybe behind here got more network, and somehow between here is also a network. What happened? If I want to go to this network, maybe yes, so my next hop is good. So I should take this path or this. Which one is the best path? How do I decide everything here? So if you have many static route, this is just for R1. Okay, for R1 to go to 4.4.4.4, I configure a static route point to R2. At R2, I also need to configure 4.4.4.4 a static route point to R4. Okay, if somehow there's a network here, after 4 also need to configure a static route point. R2 also static route point, static route point. Okay, so if I have another route right here, so I can have two routes. Either point my static route to this, and to this, or point to this, and then to this. So if you are using static route, there are so many works to do, so many configurations you have to do. Like this router to go to this router, also a static route need to configure. So what happened? You can, of course, you can use the default route. But what happened is this: in this kind of networks, so many routers. Default route, how you can default to where? Where you can default to until where? So it's very troublesome. A lot of workload for the engineers. If you click on the repeating, configure the static route, it may be somehow. Okay, somehow maybe this network is down. This network is down. So who will tell you? If this network is down, you have to go into R4, delete the default route. Go into R2, delete the default route. Go into R1, delete the default route. You have to go into 3 routers just because of one route, one network is down right here. So this is very troublesome. So is there any way can help you, can let the router to negotiate among themselves, to communicate among themselves? They advertise a network to each other. Okay, when I have a new network, I tell R2. R2 also tell R1 about the new network. It's good. When the network is down, R4 also tell R2 the network is down. Please delete from your IP routing table. R2 also tell R1, please delete the network from your routing table automatically. Okay. Then there's very less workload for the engineers. So this will it be better if you have such a technology? This is what you call a dynamic routing protocol. and the best and the most famous dynamic routing protocol we use in IGP inside the AS is OSPF and ISIS. These two. So that's why we will learn OSPF today. Okay. So what we want to learn is we want to learn how OSPF form neighbors. Okay, router 1 and router 2. Okay, we are neighbor. We can share network information. Router 2 and router 4 neighbors. They can share network informations. Okay, tomorrow we'll see how they do it. So means all the dynamic routing protocol is to automatically share their network, and if there's some network is down, they can also tell their neighbor the network is down. So everything is means that if the route is invalid, is failed, they can automatically adapt to the topology changes. So it will make the engineers administrator jobs more easier. If your network is just like ISP, there are many routers. If you are just inside a small company, maybe you're only one router, only one core switch. You are configuring the VLANs. All this, maybe you doesn't need to use the OSPF. You can use static. It's enough. Enough. So it depends on your network scenario, what you want. Okay, depending on different scenario, you apply static route or either static route or the dynamic routing protocols. Okay, so we stop here today. Do you have any other questions?
Yes, Mr. Bear.
Hey, Lucky, yes.
Yes, please. My name has not yet been added on the WhatsApp group. So whatever has been shared is that I have not been receiving anything.
You mean your name is not in the WhatsApp group?
Yes, my contact.
Oh, you are not in the WhatsApp group yet. Okay.
Yes.
Do you have your phone now?
Yes, my phone number.
Or can you just open your WhatsApp and just scan this to join the group? Can you see my share screen, right? Can you just open your WhatsApp and scan this? Oh no, you should just use any QR code reader. It's okay. Maybe your camera also got a function. If not, you can install one of it.
Okay, can I short it this way?
Sorry, again?
I just think maybe I should give you my contacts.
Oh, so can.
Yeah. 070.
Wait, wow. The IS training.
Even some of my colleagues too. Other two of my colleagues too, they are not in the WhatsApp platform too. Hilebo Ehimen and Edwin Oju, all from Igbenedion University.
Okay, never mind. Now you give me your number. I do it for you.
Okay.
070.
Yeah, 66. 24. 29. 35.
Okay.
I repeat, 070 66 24 29 35.
Okay. So is this include the country extension code? Right.
That's my WhatsApp contact. But I think Edwin and him, they should be hearing us now. If they can call their own phone number for you.
Okay.
Hello, Ahilebwaime.
I can't even scan the scan code is not working. Hello? Mr. Ben.
Yes.
Yeah, I couldn't scan the scan code. Now it's not still working.
Code is not working.
No.
Oh, sorry. No, this one. Sorry, not this one. Okay, sorry. Oops.
What do you mean?
This one. Sorry.
No. I didn't meet you. That one I get on. I'll call you back.